Hello, and this is Charlie, and we're going to go ahead and get started with the heating section right now. I'm only going to be covering the, how we create fire, how we move fire, and forced air furnaces. It's just too long to be getting into hydronic, steam, and everything else. So I am going to go ahead and do that in another session, probably in a couple weeks. Okay. So the first thing we should be talking about is, again, definitions. It seems like I always want to start there. BTU, British Thermal Unit. You are expected to know what that acronym means. You're also expected to know the definition of it. All right. And down on the bottom there, 1 BTU is the amount of heat required to raise 1 pound of water 1 degree Fahrenheit. So those are going to be the two magic numbers that we're going to want to remember. 1 pound of water and 1 degree Fahrenheit. Now, when they talk about the amount of energy, what they're really talking about is how much fuel am I going to be using in order to raise that 1 pound of water 1 degree Fahrenheit. So whether that fuel is natural gas, propane, electric, wood, oil. Now, we don't have the ability to measure the amount of wood that we use other than tossing a log on something. And same thing kind of goes with any other hard fuel like pellets or coal. Even oil is kind of limited on how much it goes through. But with natural gas, which most of the Chicagoland area here we have, we actually have the ability to measure how much gas gets used to create the fire. We can convert that amount of gas that's being used into BTUs. So on my website, thehomeInspectors.com, and then if you go under education and employment there, you're going to find a link to a gas timing chart on there. And basically it measures in seconds how many times it takes one of those dials to spin around, whether it's half pound, full pound, whatever. And each one, however many seconds it takes to do one full revolution, correlates to how many BTUs are being used of natural gas. So what's nice about that, if you want to go a little extra, a little overboard, you can look at a 80,000 BTU furnace, for example. And I don't have the numbers memorized, but let's say it takes 60 seconds to go through a 1 pound or a 2 foot-pound circle. We could go ahead, and then if we know that the furnace label says it's 80,000 BTUs, we could run that timing chart, and as long as it matches up, we're good. If it goes too fast, we're burning too much. If it goes too slow, we're burning too little. But nonetheless, I'd like you to commit this to memory. This is something that we're going to be using throughout today. We use it on air conditioning. Basically, anytime we want to take heat or, absorb heat or discharge heat, we're going to be referring to those as BTUs. All right. Next thing is going to be the fire triangle. And some people refer to this as the fire tetrahedron as well. These are the three things that we need to go ahead and make a fire. So number one is fuel, whether that be wood, gas, propane, oil, whatever it may be. We need some sort of fuel that we can burn. We do need to mix that with oxygen. Everything has what we call a flammable limit. So there's a lower flammable limit and an upper flammable limit. In other words, if I had natural gas and I was in 100% gas environment and I didn't have any fresh air in there at all, and I was starting to put sparks inside that gas, it would not ignite because I need to have that oxygen. I have to have the right mixture. I have to be between the lower flammable limit and the upper flammable limit. And then some sort of an ignition source. The fourth one, which is that tetrahedron, is the chemical chain reaction that happens and mixes all three of these things together. All right. Another term I'd like you to remember is something called complete combustion. Now, we really don't have this complete combustion. It doesn't really exist. But if we used 100% of the fuel mixed in with the oxygen, we're not going to have any byproducts at all from the fire. Usually when the first byproducts, or when we don't get a complete burn, and we usually don't get a complete burn, we're going to start getting some byproducts that comes out of there. So carbon monoxide is going to be our number one byproduct that we're going to be measuring for, or we may choose to measure for. We do put carbon monoxide alarms inside of our residential buildings. And I think that's important enough to say that in the state of Illinois here, we do have a carbon monoxide law. So we should be having a carbon monoxide alarm within 15 feet of every bedroom. All right. So if we start limiting the oxygen that we have in there, that's the more incomplete burn that we have. The more incomplete the burn is, the higher the carbon monoxide levels. If you start thinking about campfires, we get a very incomplete burn, and so much so that we are producing large amounts of carbon monoxide. It doesn't harm anyone because we're outside, but we're actually getting to the point where we're producing smoke as well. So fuel, heat, oxygen, I would like you to throw in there the chain reaction, but those are the three main things. So fire triangle is the fuel, heat, and oxygen. Tetrahedron, we're going to add the carbon, we're going to add the chain reaction to it. So the next few slides are, just more designed to be somewhat humorous, but also a little bit of an eye-opener, all right? Now, again, we're going to have oxygen and the fuel. In this drawing or illustration here, the wood that we're creating the fire, that's our fuel. The fresh air is the oxygen. Now, the radiant heat is moving the air upwards, or I should say the heat is moving it upwards through convection, which is going to actually cause a cold air to come in from underneath. That cold air coming underneath is going to be our combustion air. We do need to remember that word combustion air as well. So when the fire is radiating off, and we're going back to the caveman inventing fire stuff, forgive me for digressing so much, but he's warm in the front of him. And because there's kind of a cold draft that's coming in to go ahead and feed that fire with oxygen, his back is actually going to be cold when it comes in there. So the caveman ends up getting a little bit smart, or sort of smart, and he takes that fire and he starts putting it inside. All right. So granted, it's inside, but it does a few other things too. So we're getting our oxygen in through the openings so we could still make the fire. If we lose the oxygen, well, obviously we need oxygen to breathe, so he's not going to be living too much longer. But more so, we have the fire is going to radiate off the walls and then bounce back, and this way it keeps the front and the back of him open. The front and back of him warm. However, with the smoke and everything else that's there, we're afraid that we're going to asphyxiate this poor guy, so we don't want to leave it at that. So we take the next step and we go back to the Indians. All right, they went ahead and put fire inside of the teepees to stay warm in the winters, and they actually did well with this. The trick with the teepees, though, they were actually open on the bottom so that fresh air could come in through the bottom. The heat would then radiate and hit the sidewalls of the teepee, come back to the person. We had it open on the top so the bad gases can come out, and we don't asphyxiate anyone, and we keep getting fresh air coming into the teepee to keep them warm. Then all of a sudden we start bringing these in the houses, and we do the same thing. Typically they were with fireplaces. Now we're getting into the modern day heating systems that we have right now. We take a fire, we put it inside of a metal box, maybe a wood stove or something like that, or like I said, a fireplace. That wood stove, the metal around the wood stove gets really hot. That radiant heat bounces off and goes ahead and heats up the walls of the house, which in turn reflect that heat and keep us warm on both the front and the back on both sides. We still have a lot of waste byproducts from the fire, so we need to kind of channel that away. And we finally evolved to the point where we're putting chimneys and flues, and we're directing all that bad gases out of the house. All right. So if we break it down to the bare bones minimum, and we take this wood stove, in all reality, this is what we would refer to as our heat exchanger. All right. So I have a fire inside the wood stove, or inside that heat exchanger. That fire gets the metal of the wood stove, or the metal of the heat exchanger extremely hot. That heat now is going to start heating up the fresh air, the clean air that I breathe. We're going to separate the bad gases and the bad fires and the byproducts. We're going to separate that from the air that we breathe. And then that bad air is going to be exhausted out through the chimney or through the roof of the house. 3 more words. If you don't know what these are, I suggest you write them down. We are going to be using them again. So these are the 3 different ways that we move heat from one location to another. As we mentioned earlier with that wood stove, radiation, that heat is going to basically be going in a straight line. It's, I like using the sun as radiating heat as a good example, because we can all relate to when I'm out in the sun, I feel it hitting me, I'm nice and warm, I'm actually feeling like I'm getting a suntan, or obviously me, I never tan, but that's beside the point. But yet if I walk into the shade and I get out of the beams of the sun, I start to cool down because it's not directly hitting me anymore. So with radiation, I can actually block that heat just by putting a wall or a barrier between one object and another. So it goes in a straight line. It will reflect off of things. It will bounce off of things. But mostly it goes in a straight line. Convection, anytime we move heat through water or air, we're going to be calling it convection. So in furnaces, we have ductwork. We heat up the heat exchanger. We blow our circulation air around the heat exchanger. We absorb that heat. The fan blows it through the ductwork into the rooms where we want that heat. That's moved through convection. Hydronic heating systems. We use water. So we heat up the water. We pump the water to another radiator, another location. We move the heat from point A to point B through water, hence convection. Conduction is going through a solid. Just the fact of having the heat exchanger with the fire on the inside, the heat exchanger or the heat transferring from inside the heat exchanger to outside the heat exchanger, that's a solid material of metal, and so we're going to call that conduction. Every time I see this slide, I always go back to the Home Alone movie where you put that little heating element on the door handle and Joe Pesci touched it on the other side and burned his hand, and again, I just keep thinking conduction, move it from the inside of the house to the outside, whatever. It was funny then, but obviously I'm not any humorist. So gas feeds will be the next thing that we come up with, and I'm going to talk about gas, propane, and oil before we get on into the furnaces. All right, so here's a typical gas meter coming into the house, and not all areas have this. Here in the Midwest, it's very common that we use natural gas. I know there's a lot of areas that use propane. We still do have fuel oil in our area. I still see those trucks driving around, and I run into old tanks, even though they're abandoned and left alone. But we do run into old tanks and crawl spaces and so forth. But we'll get to that in a little bit. So as the gas comes in, one thing about natural gas in our area anyway, it's pretty clean. They do a good job baking out any humidity, they being the gas company. They get rid of the humidity, they kind of heat up the gas and get it nice and clean and dry. It gets filtered as it comes through the systems. For the most part, gas is kind of run at pretty low pressures, at least in residential areas. If you start getting into commercial areas or where the big main feeders start going before they disperse and downsize down. I remember when I was on the fire department up on Lake Cook Road, we had an open gas pipe that was leaking, and that had to be like a 50 to 100 pounder. I've never heard such a loud noise and gas spewing out of there like there was no tomorrow. We actually had to zone off a big area before the gas company came there to shut everything down so we can make it safe again. But usually with residentials, we're going to be coming into a residential neighborhood somewhere around 4 psi, plus or minus. So that pipe, this one right here, oops, sorry about that. So this pipe right here as it comes in, this is where the gas comes into the house, all right? And as it goes up the line here, this is going to be our shutoff valve or our isolation valve for the house. We do have to document in our home inspection reports the location of the main shutoff of the gas lines. That's actually in our SOP through the state of Illinois. So we come up here, it's typically 4 psi, and we're going to come into our regulator. This regulator is going to lower the gas pressure down to, I believe it's 1/4 of 1 psi. And on the bottom here, you're going to see a little opening, and typically there's going to be a screen under there too. That's a pressure relief valve. So if for some reason that there's a surge of gas pressure that comes into this gas meter or towards this house, instead of pushing that gas pressure into the house, what we're going to do is discharge the gas to the outside. I have personally never seen and I should back this up a little bit, I've never seen doing a home inspection or in my own home where we were spewing gas coming out of there. Now, in my neighborhood or when I sit on the porch, every now and then I'll get a whiff of gas. I don't know if it comes from our house or the neighbors. I can't seem to source it down. Every time I get the gas detector out when we smell it, whatever happened, it stopped. All right. Going back to the fire department, though, I have seen where these things have failed, especially on commercial properties. They open up and they stay open, and it just starts spewing gas out of there. Now, obviously, that's going to be a problem. So we come back in, 4 psi, the pressure reducing or the regulator will lower it down to 1/4 of 1 psi. Then it comes to our gas meter. These dials on the gas meter is what I was talking about. You timed as those go around when you do the gas timing chart. And again, you can find that up on our website. And then it comes up through here and then into the house and comes forth. So what belongs to the gas company and what belongs to the homeowner, you can see up here is kind of the last part that was painted, this universal fitting. So everything to the right of that that's not painted, that belongs to the homeowner. The gas meter regulator pipes that go down into the earth, that belongs to the gas company. Now, this pipe that we have above ground will be metal, all right? But this metal pipe goes into the earth maybe a foot, maybe 2 feet. It doesn't go far. Most of the gas pipes that we have underground are all going to be plastic, all right? One of the questions I like to ask people when they start in this business is, should we ground our electrical system to the gas pipes? And a lot of people look at me like, what, are you crazy? No, because if there's a spark, it's going to explode. That's not the right answer, all right? We shouldn't, again, if we have 100% natural gas, it's not going to explode, even if I start getting sparks to it. If I have a leak, that's a problem, and any spark nearby that leak can create it, but a grounding isn't going to do that. The main reason why we don't ground at the gas pipe is because it's plastic. I don't get a good connection to the earth. All right. The last thing is going to be this tracing wire, this yellow wire that wraps around the pipe here. All right. I'm sure we've all heard of Julie or whatever it's called in your area. Here it's 311. So before you dig, you want to get the joint utilities out there and mark where everything is. So because the gas lines are underground and they're plastic, we can't use a metal detector to find where they're at. So this wire wraps around that plastic gas pipe, so they could put I think it's called a sonde. They could put something where it creates a signal, and then they could run their finder or whatever that's called over the top of that, and they can mark exactly where the gas line is so that we don't dig into it. All right. So short review. Gas and then comes in through a plastic pipe, switches over to a metal pipe. That wire that goes around it is a tracing wire. Our shutoff valve. We go to our regulator. We usually go from 4 pounds to 1/4 of a psi. And we go ahead and run our meters so we can pay our bills, and then it comes into the house and feeds our gas appliances that we have inside the homes. All right. So as it comes in, just a few more terms. When I have a whole bunch of pipes together, we call that a manifold. Whether it be inside of a furnace, a water heater, whatever the case is, just referred to as a manifold. Anything that goes down is a drop. Anything that goes up is a riser. Anything that goes down at the bottom of the drop, we're going to want to put a drip leg or a sediment trap in there. All right. One of the nice things about doing these home inspection classes and the live, I get to meet a lot of people that have a stronger expertise than I do in many different fields. And just recently, we had a natural gas guy coming out there, and because for me the drip leg, I always thought of it was, when we use pipe dope to put all these pipes together, we're going to get a little bit of garbage, a little bit of debris, and I want to give that a place to land so that it doesn't come in and clog up or ruin my gas valve. All right. But he was explaining to me that they do have some issues where moisture and water gets in there, and you have to have that drip leg because sometimes they got stuck where the gas valves were in the open position and they couldn't shut down because of rust and corrosion that was there. That made a lot of sense to me, and it put a lot more importance to the fact of having a drip leg in there. All right. But mostly it's just to catch the garbage. I don't know anybody other than this gentleman who gets called when there's problems. So he gets identified, he can go ahead and see these, identify what the problem is, and fix the problem. He's the only one that I ever ran into that actually had to open that up, drain it with the water, and go ahead and close it back up again. So for him, it has happened. But other than him, I've never heard of anybody else doing that. All right. Risers, drops, drip legs. Those are going to be our main things here. Good. All right. Typical assembly when we come in there, from the right-hand side is our gas feed coming towards our furnace. Every appliance should have its own isolation valve. That isolation valve should be within reach. That is, and we have to kind of do a little bit of imagination, because when it's all together and working and we don't need it, we're not going to kind of figure things out. So we have to look at the order of things as well. That the whole purpose of that isolation valve is so I could turn the gas off and then disconnect the furnace for whatever reason. And if I have to put a new one, I could put a new one in there. All right. So gas cock, union coupling, drip leg, and then come into the unit. Now this one here, the furnace is off on the left-hand side, and the gas is actually coming from above. So using our pointer again, this is where my gas is coming in. We go to our drip leg, and then we go to our isolation valve, and then I go over to my furnace. All right. But if you think about this, if I have to disconnect this, so I turn the isolation valve off, and then I go ahead and disconnect this, well, I got no way now to turn the gas off, so I'm just going to be leaking. So this was, we found this on one of our field events. And again, it's real easy to walk by some of these things because everything's working normal, and it just doesn't come into the brain to start thinking about the order of stuff. So you kind of have to pull things out there. We want to make sure that our isolation valve comes before the drip leg, before the universal fitting on there. Flexible gas appliances. I can't tell you how many times I see people using these things and using them wrong. All right. This slide might not have all the rules that are on there. I would like to make sure that we do understand most of the rules, if not all of them, when it comes to these gas appliances. Number one is the length. All right. And I don't think they sell gas connectors longer than 6 feet anyway. I know you could buy CSST stuff, but not gas connectors longer than 6 feet. We can't daisy chain them. All right, so I can't take one 6-footer, put a fitting in between them, and another 6-footer to reach my appliances. Maximum length 6 feet. Even if I get two 2-footers, and that's only 4 feet, which is still under my 6-foot mark, I can't do that either. So we can't daisy chain these things together. They can only be used once. So once an appliance has been removed or disconnected, the entire gas connector is supposed to be thrown away and a new one installed for each one. They cannot travel through a structure or a wall of any type. So in this diagram, we're showing where the gas connector comes in from the room to the right or the cabinet to the right, goes through the wall, and then behind the stove in there. Even if it was like a furnace, you can't even run the flexible gas connector into the furnace and connect it there. You have to have a steel pipe coming out of it, and then you have to connect the gas connector to that one. Shut-off valve should be in the same room, wherever the appliance is, and even when we're dealing with cabinets, the shut-off valve should be in the same cabinet, wherever the appliance is. All right. It can't be concealed. No, it's a little misleading. It could be concealed, such as behind the stove where you can't see it. But what we're saying is you shouldn't have to build a little chase, like a soffit box or something, and run the gas pipe through that. It shouldn't be fished behind any drywall. Everything needs to be out in the open where we can see it. Again, used one time, no longer than 6 feet. Don't daisy chain them. Cannot go through a structure and cannot go through an appliance wall. Just a simple flexible gas connector. We have the shut-off valve in the basement. They ran it to a stove upstairs. Instead of running black pipe coming up there and putting the shut-off valve upstairs, we ended up doing it downstairs. Obviously, it's wrong. Old brass ones like these, they've all been recalled, and I can't tell you the last time I've ever seen one. It's going to have to be on a pretty old house. Most of the time, the appliances failed, and people have had to put a new one in there. Yeah, it is what it is. In the Chicago area here, it's very common that appliances such as water heaters and furnaces are all black pipe, straight into it. We don't use appliance connectors, all right? However, most codes, especially in the suburbs, do allow it, all right? And it's not necessarily a bad thing. It can't go through a structure, but it can connect a water heater or a furnace. So that doesn't mean it's necessarily a bad thing. However, I would still be a little bit suspicious. It's not a common practice that we do this. Coated stainless steel or CSST. These are flexible gas lines. These are designed to go through. These are designed to go through structures per se, and they usually will have a manifold right where it comes into right where the gas enters the building, and we're going to have one of these lines going to each one of the different appliances, and there'll be a separate shutoff for each one of those lines. Part of the problems, and I've actually been on a couple of fires where this has happened. A couple of problems with CSST is if you don't ground or bond these things properly, and the house ends up getting struck by lightning, then we start getting sparks. They don't do a good job because they're very thin, they don't do a good job at dispersing the electricity that comes from the lightning strike. So if they're close to a plumbing pipe or a grounded appliance or anything like that, then there ends up being a spark between the pipe and the appliance. And that spark, we're talking a lightning strike, so it has a tremendous amount of power. What's been happening was it creates a hole in that pipe about the size of a pencil, all right? But a hole the size of a pencil at 1/4 of 1 psi is pretty powerful. And then all of a sudden it starts spewing a whole bunch of gas into the building, looking for an ignition source, whether spark from light switches, furnaces, water heaters, dryers running, whatever it may be, even a hot light bulb for a reason. And it's been the culprit for burning houses down. And the two that we invested in pipes, and the house probably got struck by lightning. So we're supposed to have these things bonded, and typically on both ends of them, because they're not strong enough to conduct the electricity. So we need to give that electricity a pathway someplace else to get to the water pipes, and then get it out of the house. All right, CSST. The yellow stuff is the one that needs to be bonded. I believe they came out with the gray one now, and that does not require bonding, but I would have to do a little bit more research on that one. So I do want you to look up the color coding for the yellow CSST and the bonding requirements on that as compared to the gray CSST. And this is what I was talking about, the manifold. This is what we commonly see. So gas comes in. Looks like we got 5 different gas appliances. We run one line for each one of them. Looks like they wrote on there exactly what it is. Typical manifold with a shutoff on each one of them. Looks pretty good, but it's not bonded, at least not at this end. Teflon tape on gas pipe is basically a no-no. I don't have any history or knowledge where these things have actually failed putting Teflon tape on there, so I can't speak to or against it at all. But rules are rules. We don't make these type of rules unless something did happen. So usually it's going to end up being pipe dope is what we'll see on there. Now there is a Teflon tape that is made for gas pipes. It's yellow in color, and that's supposed to be its identifying mark. I have seen that, and it fades to like a creamy white after about 10-15 years. And this white Teflon tape kind of fades to a creamy yellow after about 10 or 15 years. So it's not always going to be brand new white or brand new yellow that you come in there. Sometimes we're going to be a little bit confused when it comes to it. But yellow Teflon tape is okay. White Teflon tape, no way. And preferred, and so there's no mixture, is going to be pipe dope that comes in there. So if we look to the right where the gas meter is, and again we'll come over here, and this fitting down here as well, even down below, oops, I can't get down there, but even the one below the dot, those are all the yellow Teflon tapes. And then what we have up at the universal, it looks like this one is yellow as well. And then I'm not sure if somebody just replaced this pipe in here. Maybe they needed to make it longer or shorter for whatever reason. And now I'm seeing the white Teflon tape in here. Again, I'm a big fan of using gas detectors, and we would take our little Klein tool and check each and every joint when it comes in there to see if it's leaking. Because it's not allowed, I just don't want to take ownership of things. So these are things that I do document if I see the white tape on there. But I can't, I don't know, maybe I'm wrong, but I just can't in my right mind tell someone, undo this, put the pipe dope in, or the yellow tape in there, because it's the raw material that was used. Unless I have some sort of intimate knowledge that this has created problems, and I just don't have that. I just don't believe that it happens. But I'm still going to tell my person that it's not, or my client, that it's not allowed. And if you want to be safe, then go ahead and change it out. That another good reason is when you go to sell this house, if anybody's on their game, they'll probably be calling it out then too, and somebody's gonna maybe make an issue out of it at that point. We all have different opinions when it comes to stuff, and whatever our clients hear and how serious things are, that's kind of up to them. So, galvanized pipe. It's not the best practice. Everything should be black iron. All the threading and the sizes are the same when we're dealing with galvanized pipes. And when I first started in this business back in the 90s, it was somebody, I was told that, the galvanized pipe is going to leak, and, it's going to corrode with the gas inside of it, and the fittings are going to go bad, and you're going to burn your house down. And, I've been in the fireman business for almost 40 years, and I never run into a house that caught on fire or heard of another investigation that showed that it was galvanized plumbing that came in there. All right. And for me, it was just something I always called out. And I had this plumber one time, and he just lit me up like there was no tomorrow. And it was really old guy. He was real short, maybe about 4 feet. And I stand about 6 feet tall, so, I was over him quite a bit. And I don't know if you could picture those old Mickey Rooney type guys with a cigar in their mouth. It's not lit, but it's been there for like 10 years or so. And that's what this guy, and he starts pointing me and poking me in the chest like he wants to start a fight with me. And again, he was like in his 70s, and at this time, I think I was in my 30s, maybe early 40s. And he's pointing up at me and using a few colorful metaphors, I said, never once have I ever seen where a gas pipe was leaking from this. And I started thinking, I'm like, wow, the guy's right. So I don't call this out anymore. I'll identify it, but really that's about it. Now, I do know there's a lot of suburbs in our area that do city inspections when there's real estate transfers. And North Lake actually came to mind, and I don't even know if they still do this or not, but North Lake has it in their transfer protocols that all gas pipes have to be black pipe. All right. Now, I interpret that as being black iron as the material, but their interpretation of it is color coding. So they're okay if it's black iron. If they do see galvanized pipe like this, then somebody has to paint it black, and that's their solution to that. So again, I'm going to stick to my opinion, and that's all I'm doing is sharing that, is that galvanized pipe really isn't that big of a deal when I see it, but I'm still going to go ahead and identify it. Drip legs, we talked a little bit about it already. Anytime I have a drop, we want to give away for the sediment. If there's any oils or moistures or anything that's in there, we want to go ahead and give that a place to collect so it doesn't come into the gas valve and damage our gas valve. This water heater, I don't know if you could see it down there at the bottom, right above the cursor here. There's actually scorching coming out of there. So that's a pretty good indicator that either we're depressurized in the area or we have a very bad gas-air mixture and the fuel is spilling out of the opening and igniting and causing that scorching to be there. But we'll talk about scorching in a little bit. Propanes, for those of you in the rural areas, I'm not going to go too crazy on this. I do want you to know propane is far more flammable than natural gas is, all right? And I do believe propane is a mixture. It's not just one gas. I think it's butane and propane. There's a LPG, liquefied petroleum gas, and it's some sort of mixture between the different fuels that they go ahead and create. Now, typically one tank, when they go ahead and fill it up, they're supposed to be big enough to get the house through one heating season on normal use. Sometimes it works, sometimes it doesn't. So usually in the beginning of the heating season is when these things get filled up. They do have to be kept away from the home. And on the next slide I'll go ahead and show that distance. But going back to the flammability thing, if you do convert from propane to a natural gas, in other words, if I take a propane device and I hook it up to natural gas, like let's just say a propane grill, and I decide I want to run a gas line out there to this one so I don't have to buy those tanks again, and I hook it up, I'm going to get a real bad flame coming out of there. Very little fuel. It's going to be very limited on what comes out of there. I'm not going to get a lot of heat coming out of it. It's not going to be able to cook anything. I have to change the regulator out of it so that I could allow more fuel to pass through of it. And even the orifices, all right? So where the gas shoots out before it pulls in the oxygen and mixes with it, the propane orifices, because they're more flammable, they're under a higher pressure, those are going to be smaller. They're going to limit the amount of fuel that's going to shoot out of there. The gas orifices are going to be bigger so that more fuel can come out of there. All right. I have heard of that as being a test question, but if somebody says they put their grill on there on the natural gas and now they don't get any heat, that's the reason. The orifices are too small. Same thing if I bought a furnace that's designed for natural gas and I put it on a propane heater, now I'm going to have too big of a flame because those orifices are going to be bigger and we're going to be putting a larger pressure in there. All right. All right, just our distances. Small tanks, they need to be 5 feet away from the house. Medium tanks are going to be 10 feet away, and that big tank that I showed you, which is pretty much a 2,000-gallon tank, those have to be at least 25 feet away from the house. So usually they're going to run the lines below grade and then come back up into the house. And then you could also see our distance to, ignition sources and property lines. Now, our ignition sources are going to be outlets, air conditioning compressor units. If you have an outside distribution panel, that would be considered an ignition source as well. So appliance cannot be located in a basement or pit. It has to be vented to the exterior. What else we have? Propane, like natural gas, is odorless and colorless. So you're going to need a natural gas detector to go ahead and sense that. It does require 2.5 times the amount of combustion air as compared to natural gas. Because it's more flammable, because it creates a fire, the more fuel we have, and the stronger or the more rich the fuel is, the more oxygen I have to put in there. That's its rationale behind it. All right. Oil feeds. And again, we don't have too many of these things, so I'm not going to hit these really hard. We're just going to give the quick chats and stuff we're looking for. So first thing is identifying them. Typically, we're going to have 2 pipes. One's going to be our fill and one's going to be our vent. Once I put liquid inside of a tank, I have to let the air that's in the tank get out of it. And in order for the liquid to come out of the tank, I have to let more air come back into it. All right. These tanks are not under any pressure, so they're just gravity fed, and that's it. In our area, if we have an unused, buried storage tank, it has to be removed. It's not cheap, and especially if it's leaked in the past, then it gets pretty expensive. So the guys that go ahead and remove these tanks, they're going to dig around the area, remove all the soil, especially anything that could have been polluted with the oil. They're going to make sure all that soil is removed as well. Then they have to come back and put additional stuff back in there. So typically in the Chicagoland area, I think they were quoting somewhere around 10, 20,000. And that was maybe 5-6 years ago, so I'm sure the price has gone up since then. It's not a cheap thing to do. And that's only if it's buried in the earth. It doesn't mean that it's below grade. So if you go into a basement or a crawl space and you find an oil tank there, that's going to be up to your client. There's nothing that says it has to be removed. Sometimes it's actually more dangerous to remove it than anything else, just because the only way to get it out of those crawl spaces is to cut it up into smaller pieces. And when you do that, you've got a chance of making sparks. And if there's any oil fumes in there, you're taking a good chance of exploding something at that point in time. So if you do see any sort of oil pipes coming outside, the fill pipe will be bigger than the vent pipe coming out of there. It's going to be a good clue that we have oil or had an oil storage tank on site. All right. This was a house that actually had it inside the crawl space, and you can see the pipe coming up with the cap on it. That's our fill pipe, and then the one going down is our vent pipe. And we did have an oil tank inside there. If the oil is being used, it does need to be kept away from any ignition sources. So again, outlets, furnace, water heaters, anything that's going to go ahead and create a fire. Minimum distance is 10 feet. A lot of times we'll see in our area, there'll actually be a wall that gets built because we know that there's a spill, it's going to be a liquid, it'll be on the ground. And if it's air, it's heavier than air, so it's going to stay down low as well. And we don't want to let that make its way over to where the ignition source is. So 5 feet if there's a wall, 10 feet if there isn't. When we send our fuels into the flue, we have to dilute that air. So I used the term of combustion air before. Combustion air is the air that I need to mix with the fuel to make the fire. As I make the fire, I'm going to get to certain temperatures. Typically, oil is going to be closer to the 600 to 900 degree mark. And when that happens, we need to put in some cool dilution air with it. In oil systems, we're going to be using something called a barometric damper. Now, that little weight on the bottom of this thing right here, that is basically designed to keep it closed. And as the hot air goes up and through that pipe, the hotter it gets, the faster it moves. The faster air moves, the pressure actually drops. So when we lower the pressure, we create what's called a Venturi effect. And then this door gently opens and starts letting in 70-degree air or dilution air, and that mixes with the hot air that's going up and out, so that brings that temperature down. Now this thing's designed where it's going to find that happy place, so as it slows the venting down, it's going to get to a certain opening. Too fast, it opens more. Too slow, it closes, until finally it gets at a happy point. That opening, that damper, should be very easy to move. All right, it should. If it's rusted at all, and I wouldn't touch it with my hand on there, I would just give it a tap with a screwdriver or something and make sure that it just swings freely and ends up coming back closed when it's not in use. But if it's rusted, stuck in the open position, stuck in the closed position, obviously that's a problem and it needs to be corrected. Oil burners, don't know what to say about these things. Everything is kind of confined. So unlike natural gas, which comes into our house under pressure, and even though we lower it to 1/4 of 1 psi, same thing with propane, it comes into the house under pressure. Oil does not. All right, oil is in a tank, and it's just going to be gravity and a liquid that comes through it. Now, and then it'll create a siphon to pull more oil into it. Now, these burners are pumps. So the motor is going to be spinning. It's going to be blowing air into the unit. It's going to be pressurizing that oil as it comes through the pipe, and then once we pressurize the oil, it sends it to a thing called an atomizer. So it creates a real fine, thin mist, mixes it with combustion air from the room that blows in with that, and then we could go ahead and ignite it. We have a lot of surface area that's in there, and we usually get a pretty decently clean burn coming out of these things. When they're working properly, they should be relatively quiet. If you put your hand on them, you might be able to feel them spinning, but you really shouldn't be hearing anything. If you do, obviously we're getting bad bearings or something's getting ready to go wrong. Maybe you can get by with just oiling it, but nonetheless, it's something that needs to be corrected. All right, and they need to find out what it is. We shouldn't get any smoke coming off of these things. We shouldn't have any scorching. We shouldn't have any soot that's being brought into the chambers or the heating units on there. They should be making a relatively clean burn when it comes to it, just like natural gas. Right. So things to look out for: 24-inch clearance between the burner and the combustible materials. Okay. The ignition transformer shouldn't be vibrating. Everything should be smooth. You'll find that dirt gets put around this air intake port right in here. And so that should be clean, so we don't limit the amount of air that comes into it at all. There should be no oil leaking from any of these joints in here, so our pump should be working just fine. If you could see the flame do anything else, it should be more of a cone shape than anything else. Typical color is going to be yellow and orange when it comes in there. The primary controller, all right, the purpose of that is kind of like a reset button. And so basically our pump, our motor kicks on. So our thermostat calls for heat. Our motor kicks on. We start spraying oil into the unit. We're blowing oxygen in there. Our igniter is sparking. And we should start a fire. If we don't sense the fire, then the unit's going to shut itself down. The only way it's going to restart again is to go press this primary controller button and get it to restart again. All right. I'm going to suggest that you don't do that, and the whole reason is we don't know how many times that button was started. It's not our problem. I always remember, somebody once saying that, if this thing's broken, that's somebody else's problem. But if I start messing with it and trying to fix it, now I end up making their problem my problem. And it's not my problem. My job was to identify things that aren't working. Now, granted, if you're intimately familiar with these things and you know your way around them, have at it. You're a better expert than I am. But if you do have some weaknesses on them, like I do, then I wouldn't be resetting it. We turned it on. We made our attempt. It didn't operate, whatever the reason. It could be a bad igniter. It could be that I got dirt around that air intake, so I'm not getting any oxygen coming in there. It could be my pump is bad. It could be I'm out of oil. It could be a whole bunch of stuff. But if somebody went in there and they tried to restart this thing, and maybe they did it 3, 4, 5, 6 times, and now I go do it again, and now there's a whole bunch of oil that's in there, and I don't want to take a chance of an explosion or anything else like that. I'd rather just plead ignorance and say I don't know, it's not working. Let's get a heating guy that's familiar with it to go ahead and fix it. Combustion air, I kind of used that term a little bit earlier, but we need to be checking for combustion air as it comes into our appliances to make sure they're working, or our gas appliances. So when I use the term appliances, I am talking about the furnace, the water heater. I'm even talking about a gas dryer or a gas stove. All of those, we're going to lump them together as appliances. Now, there are basic general rules of thumb to make sure that we have enough combustion air. So if I have a room that's big enough, I don't have to bring combustion air from another location, all right? And I'll show that slide in a little bit. But let's say I am in a small room and I want to start drawing combustion air into where our furnace is. Now this is a natural draft furnace. So up on top here, we do have a draft hood. There is no fan inside there. I'm not creating a draft when it comes through it. Combustion air is going to come in through the bottom, and that's what I'm going to be mixing with my fuel to go ahead and make my fire. The dilution air comes in through the draft hood, and that's what I'm going to be using to lower the temperature as it goes up and out the chimney. So combustion air where the fire is, dilution air where it goes up and out. We do need to look at the data plate that's on the furnace. You're going to find 2 numbers on the data plate. One number is going to be for the input BTU, and then there's going to be an output BTU. So the input BTU is how many BTUs I'm making with those burners that are there. So if I have a 80,000 input, or I'm actually going to use simpler numbers, 100,000 input BTU, all right, and an 80,000 output BTUs, that tells me that I have an 80% furnace. So 100,000 BTUs is made to create the fire. 80,000 BTUs are going into the house. That's my output. The other 20,000 or 20% is going up and out the vent. That 100,000 BTU is the number that I'm going to be using for my combustion air. If I'm taking combustion air from an inside source, all right, from another room inside the house, I can do that. I just need to have two openings that bring it into the house. So 1 square inch for every 1,000 BTUs up high, and 1 square inch for every 1,000 BTUs down low. So if this is a 100,000 BTU opening, I need to have basically a 10 by 10 opening. Now, because these grills eat up those spaces, a 10 by 10 isn't going to be big enough, all right? So typically we want to be about 25% more than what that is. I think I got another slide coming up a little bit that explains how much gets eaten up. I know with the wood grills, that's like, there's only 25% comes through, where it's kind of the other way around with the metal grills. So we do need to be significantly bigger. All right, 1 high, 1 low. So 100,000 BTUs, this is kind of the same example I just used. We need 100 square inches. Metal grills use 75%, so we kind of have to add on another third to get that 100% back up there. Wood grills are 25, so I have to do quadruple, to get to the 100% of that mark coming in there. 1,000 or 1 square inch for every 1,000 BTUs. That is if I bring the combustion air from another room that's already inside the house. Now, if I have a pipe that I'm bringing combustion air from outside the house, and I guess I should be a little bit more specific. It doesn't necessarily have to be outside the house, but it has to be outside the conditioned space. All right. So if I have an attic that's vented and open to the outside, I can bring combustion air into the room through that attic. That's completely acceptable. If I have a crawl space that's part of the exterior of the house, so it's in the unconditioned space, we're not heating it, we're not cooling it, we're not insulating it, I can bring combustion air from there as well. Typically, they're going to go through a sidewall, and they're going to bring everything from there. Now, those BTUs, the previous slide was 1 square inch for every 1,000 BTUs, where in this case, it's going to be 1 square inch for every 5,000 BTUs, all right? So at this point in time, we would just have, what is it, out of 100,000, divide by 5, that's 20. So I need 20 square inches instead of 100 square inches to give me the same amount of air coming to the outside. Usually it's going to end up being like a 6-inch duct to 5-inch duct that comes out of there. We do want to have some sort of a damper on it so that, we're not losing heat. B, we're not flowing in air, cold air when the furnace isn't operating. This is only designed to bring the combustion air and the dilution air into the room when the furnace is operating. If I don't have any sort of additional combustion air coming in there, that's fine. It depends on the total amount of BTUs that's being used in that room. So if it's 100,000 BTUs, we need 5,000 cubic feet. In other words, 25 by 25 feet, based on an 8-foot ceiling. All right. The more BTUs, the bigger the room is. So for if you got an open, unfinished basement, that's a pretty decent size. And nowadays, our appliances are getting far more efficient than when we put these numbers together. It used to be like a 40,000 BTU water heater and a 100,000 BTU furnace, and we would need a 30 by 30 room in order to do that. And typically they want to have fresh air coming in from the outside. But everything's more efficient right now. We're not getting that point. So if we have an open basement, even if it's finished, as long as it's wide open, then we really don't have to have any sort of external combustion air coming in. This is a golden rule. Does need to be committed to memory. So combustion air, again, that's the air that I need to make the fire. Combustion air cannot be taken from a bedroom or a bathroom. All right. And that closet that's in the bedroom or the bathroom, even though it says it can't be taken from the closet, it all depends on how it's set up. All right. So if that door that we're looking at right now is an exterior door and it has weather stripping all the way around it, and when that door is shut, air is not passing through it, and we do have another combustion air source outside, that furnace located there is just fine. All right. If it was a high efficiency furnace with 2 pipes on it, one pipe brings in combustion air and the other pipe exhausts the used gases from the fire, I'm not using the room air for combustion air. I'm bringing combustion air through one of the 2 pipes. If that's the point, then that can also be put in there. Now, if this is a natural draft or an 80%er and that door has louvers on it or it's open on the bottom, and now I'm drawing combustion air from that bedroom in order to make the fire, that's when it's a problem. So the key word is using combustion air from a bedroom or a bathroom. Another term is scorching, and we're going to start getting into the furnaces real soon. Scorching even is any time that I'm burning something, for lack of a better term. So when in this situation, when I have it around the burner like this, that's a pretty strong sign that either I got a hole in the heat exchanger or I got one hell of a bad gas air mixture. And if I have like it's coming out of there too rich, maybe a pipe is broken and it's not drawing in enough oxygen to go ahead and ignite right away. So it pushes the gas and then the gas starts spilling out of that opening. It's going to eventually ignite, and when it ignites, it does create a flash that comes in there, and that flash is what ends up leaving the scorching marks. Sometimes we'll see rust marks on there as well. Another indicator that we're backdrafting, or at least air is rolling out of there. So scorching, flame rollout is another term that we're going to be using when the flame actually goes the wrong direction. This one's a little bit wider. You can see how it has that big cave that comes all the way across, our big arch that comes all the way across here, that's all scorching as well. Now this is on a hydronic boiler, and you could even see all the rust over here as well. So chances are we had a lot of flame rollout and it's coming up on the sides. It does bring with it a whole bunch of humidity. So, and it may have been fixed. We don't know. All we could do is identify what it is, give a probable cause, and then let somebody else come in here to do a diagnosis to it. Right. Going back to natural draft furnaces, I can't tell you when the last time I've ever done this, and I don't know if I ever will again. We used to take off the draft hoods and try and get inside the heat exchanger where the burners are and visually check it for holes or cracks in the heat exchanger. I'm going down memory lane here. I used to have this little dental mirror when I started, and I would aim it because right up on the underside or straight in the back, that's where you would find most of the holes and rusted out parts of the heat exchangers on there. And once the heat exchanger is gone, it's, you're done. You might as well just get a whole new furnace. Everything else is going to be 20 plus years old. And even with these old natural drafts, they're going to be over 25 years old. I can't, I may run into one that's still working, but I really haven't seen one in a long, long time. All right, so I think it would be very rare. But we would unscrew the flame rollout shield, get our mirrors inside of there, obviously, and look for any sort of rust, cracking, holes, and so forth. I ended up getting a plexiglass mirror. That was probably one of the smartest things I ever did. Get a plexiglass mirror that was like about 1.5 inches, 2 inches wide, and about 2 feet long. And then I would stick that right on top of the burner, and I would shine a flashlight. I kind of put the tip where my nose is so the beam follows my eyes, and it reflected off the mirror, and then I was able to see up inside the heat exchanger. And it gave me the biggest area that I could see with, and then I would tilt it up, so I get that reflection as it comes back and see the back side of that furnace. Reminiscing there. Nowadays, with the mid-efficiency and high-efficiency furnaces, we really don't even see the inside of the heat exchanger anymore. We may be able to see a small little section of it, and that's it. So we're kind of limited in what we can do with the furnaces. All right. So venting, and this next section is going to talk about exhausting our bad gases after the fire. A little more terminology. I'd like you to know the difference between a flue, a vent, and a vent connector. All right. Flues, first of all, they have to conform to the 2-10-3 rule. That 2-10-3 rule is the height above a roof line that a top of a chimney or top of a flue needs to be. All right. So in other words, it has to be 2 feet higher than anything within 10 feet of it, and the minimum height above the roof line has to be 3 feet. All right. So 2 feet higher than anything within 10 feet. But if this is my roof, I have to be at least 3 feet and off the highest end of that roof. So if it's like a 412 slow pitch and I'm almost at the top of the roof already, so there's nothing within 10 feet of it at the top line of it, I still have to be 3 feet above that roof line. If it's a real steep pitch like this and the chimney comes up this way, then whatever is 10 feet away from that, then that has to be 2 feet higher than that 10-foot point. All right. In order for something to fall under those rules and be classified as a flue, it basically one of two things has to be existing. It has to be inside of a chimney. So it doesn't matter what the fuel is that I'm exhausting. As soon as I put it in a chimney, then it's automatically a flue. When it's a flue, it falls under the 2-10-3 rule. Also, if I'm exhausting wood or oil, it's automatically a flue, and it has to fall under the 2-10-3 rule. If it's natural gas or propane, all right, and it's not in a chimney, all right, So that's our second one up in here. All right, that's for our vent right here. They have their own requirements, and they could be as low as 6 inches above the roof line. Typically, we're going to see them around 2 feet. I do see where a lot of inspectors make a mistake, and they'll see a B vent that comes up through the roof, and they start calling out the 210-3 rule. It doesn't have to conform to that, all right? As long as it's natural gas and it's not inside of a chimney, then it doesn't have to conform to that. There is a chart. I know you could find it in the IRC and under the mechanical code section where it talks about the height for venting gas appliances. And that all has to do with the slope of the roof. So the steeper the slope, the taller it needs to be. The lower the slope, the less it needs to be. But there is no 210-3 rule when it comes to that. Vents for gas appliances, if it's a high efficiency, it's going to be a PVC pipe. If it's going to be a mid-efficiency furnace, typically that's going to be a B vent that goes up in there. Even the old natural draft furnaces, those are going to be also B vents that come in there. Those B vents, we'll get into clearances of those in a little bit. Those had a 1-inch clearance where our vent connectors have 6 when it comes to gas. So that brings me up to the third item, the vent connector. This is the pipe that, let me back up. Most vents for the mid and natural draft, mid efficiency furnaces and natural draft furnaces, those are going to be a 2-wall pipe. So it's going to be a pipe, and then there's another pipe inside of it. And there's going to be a small air gap, usually about 1/4 of an inch in between there, so air is going to be able to flow between the two of them. That helps dissipate the heat so I can get closer to combustible materials. A vent connector is going to be a single wall pipe. All right, and that single wall pipe is what connects the appliance to the chimney or connects the appliance to the B vent, and that's called a vent connector. Single wall pipes, and these vent connectors cannot go through a structure. They can't go through a wall. They can't go through a floor. They can't go up and out through the roof. All right, they're just meant to connect to the B vent. They do have to conform to the same slope rules. We'll get to those in a little bit. But again, they can't go through a structure. So in this illustration, we're showing both a vent connector and a B vent. All right. So as I start over here, here's my appliance, and right above the appliance is my vent connector. This pipe is sloped upwards towards my B vent, and now I have the pipe within a pipe. The B vent can go through my structure and can go all the way through the house and all the way up through the roof. All right. This B vent, the way they're usually designed is I can get a 1-inch clearance to combustible. So even though I'm going through a structure, and this illustration kind of shows it touching, there should be at least a 1-inch. Vent connectors, this for natural gas, it's going to be 6 inches. I would like you to remember that, all right? 3 different numbers. Vent connectors can be used on gas, propane, oil, wood. They're going to be used on all of those. But the clearance from that combustible material depends on the fuel that's being burned. So vent connectors for gas and propane, and again, please write this down, 6 inches. Vent connectors for oil, 9 inches. Vent connectors for wood, 18 inches. So 6, 9, 18, those are the 3 magic numbers we need to remember. 6 for gas, 9 for oil, 18 for wood. This one's kind of a no-brainer. We're coming out of our water heater because I have a draft hood over the top of my water heater. I know that I'm going to be a gas appliance. So because I'm a gas appliance, that means I have to be 6 inches away from combustible materials. It's still supposed to slope upwards until it goes into the chimney. Anytime it goes downwards, like we're seeing in this picture, that's something that's going to limit the flow and be a high chance of backdrafting. When it comes to water heaters, when we look down at these escutcheon plates, which are pieces of plastic where the water pipes come into the water tank, they melt pretty quick and easy. So if I'm backdrafting at any time, or if I have backdrafted at any time during this, I'm going to see those things melted. Length of a vent connector, typically under 5. There has to be some sort of an offset. We don't want to be going straight up and down. You know, once we start getting over 10 feet, we need to start being a little bit worried, all right? So we're going to be looking for signs that we're not venting completely and our air gases aren't going up there. Clues that that's happening is we're going to see condensation stains on the vent connectors or on the B vents. We may see some backdrafting signs like I talked about with those escutcheon plates, but we definitely want to look for it. These vent connectors are supposed to be the same size as the opening that comes out of the top of the appliance. We're not supposed to make them bigger. We're not supposed to make them smaller. They need to be the same size. And same thing when we go up to the B vent. Now they can get bigger when they connect with another appliance. So I could have multiple gas appliances. I could have multiple propane appliances hooked up to the same vent. I cannot mix fuels, however. So if I have a gas and an oil appliance, I can't mix those exhaust gases. They have to stay separate. Just the other day, I was called for a water heater and to verify that it was venting into the fireplace flue. And, you know, I was in disbelief when the person called me and said that, you know, they're doing an insurance claim, and they want to make sure that everything's okay. And the person who's going to install the water heater said that it goes into the flue. And I'm like, well, that's not possible. People just don't do that. It was the case. So what I ended up doing was disconnecting the water heater vent connector where it went into the chimney. I ended up putting a flashlight in there. I went into the firebox and looked up the smoke chamber and looked up the flue. And sure enough, there was my beam right there for my flashlight. It was definitely coming right inside there. So there was no damage. The measurements worked out fine. There was only one flue going up and out the top. All the signs said, yeah, this is going in there. So now their solution is either to build a fireplace with a secondary flue going to the outside, or they can go ahead with a higher efficient water heater and just direct vent it straight out the sidewall. And I believe that's the route that they're going. So they're going to disconnect it from the chimney and then put that sidewall in there. So 3 screws are supposed to be holding all these connections together. They don't all have to be evenly spread out around a circle, but there do have to be 3 points of contact in a circle, and that's going to keep these things from twisting or flipping around. No openings, nothing where anything's going to become allowing carbon monoxide to enter the building, so it does need to be tight. When we put these sleeves in there, common sense says that I have to have the smaller pipe going into the bigger pipe as it goes up and out. If it's the other way around, then I'm going to leave a chance for carbon monoxide to be escaping between those 2 gaps, all right? We talked about clearances before. So natural gas, clearance on a single wall pipe or the vent connector, 6 inches. Clearances for B vents on natural gas is going to be 1 inch. Now at the bottom, down here, this whole pipe throughout here, this is my vent connector. And then right up in here is where my B vent begins. So you can see it's just a small little gap in between there. But that little gap allows enough air to go through and lowers the temperature of that metal so that I can get closer to the wood. I still have to maintain a 1 inch clearance. All right. In this case, it's actually touching. It's actually touching the wood. Now, granted, there was no burn marks or anything else on there, but it was still touching the wood, which is, going to be somewhat of an issue. Even with this insulation on the pipes or the refrigerant lines that come to the vent connectors. I just had one yesterday. Two things on the vent connector. One is they had their suit that was in one of those plastic clothing bags, that you cover the suit to keep dust from getting on it. They had that hanging on the plumbing pipe that would drape it over the vent connector, and it was literally resting on the vent connector. So I'm curious, and I unhook it off the pipe and pull it away, and sure enough, all that plastic was melted right onto the pipe. It gets that hot. I mean, luckily their clothes weren't ruined at all, but I just couldn't leave it like that, so I brought it down and moved it to another location. And then they also had their air conditioning refrigerant lines also touching the vent connector, and that styrofoam insulation, basically this stuff over here on the right, that styrofoam insulation was scorched and melted as well. All right. Now, I hear the argument saying that, well, 6 inches is kind of overkill. I've seen so many times where things are closer than the 6 inches, and never has a problem ever really occurred. And I get it, and I've seen the same thing with my own eyes. Something's been there for 15 years. You would think I would have some sort of melting and burning, just like I described, that we see, and sometimes it doesn't happen when it's there. I get it. But those distances are not there for when the furnace is operating normal. They're there when something goes haywire. All right, they're there to be overly cautious, overly protective. It's not in our, when they set up these numbers and these clearances, it's not that, well, we want to reduce the chances of a house catching on fire. No, we want to make a logical clearance distance where there won't be any chance that a house will catch on fire. So because of which, I'm kind of a stickler when it comes to these things. Anytime I see a combustible materials such as the refrigerant lines, non-metallic cable wiring that comes in there, any sort of insulation that could be anywhere, wood structures of the material. If I'm within 6 inches, it's getting photographed, it's getting documented, it's going in our report. All right, that's my 2 cents. Here's a nice one. So we got our vent connectors, and that 6 inches is straight horizontal. It's not an arch that comes in here, all right? It's going straight out to the side. So this is okay, is what we're looking at. So I got my I-joist. I'm 6 inches away from my vent connector. I switch over to my B-vent. I could get within 1 inch. I don't see any issues with that one. Here's another one. You can see that now I'm going to be within 1 inch from my B-vent to my vent connector. And actually, this is above the I-joist on this one. So because it's above, now I have to maintain a 6-inch clearance between these two items. And again, that's going to be a problem. Oil connectors. This drawing is saying 18 inches. That's an apology of me, all right? Those numbers that are written on there are incorrect. Oil is going to be 9 inches. Wood will be 18 inches. And an L vent is actually also 1 inch. We're going to get off that slide real quick so there's no proof of my mistake. Vent connectors as we come off the top. Now, people have enlarged and reduced these pipes, and there's some manufacturers that do allow for it, and the only way you're going to know that is by finding the installation manuals where it comes to it. But as far as a good general rule of thumb is concerned, they should be the same size as what's coming off of here. What usually happens is that they'll have an old natural draft furnace, and then they're going to put a mid-efficiency furnace in there, one that uses or exhausts far less BTUs up and out the pipe, so it doesn't have that heated draft that keeps it going. And they don't change out the actual vent connector or the B vent going outside. So the code does say that we have to size the vent connectors and the vents and the flues to the appliance or appliances. All right. So the more BTUs, the bigger it needs to be. The smaller the amount of BTUs, the smaller it needs to be. If I take an old furnace and remove it and switch out a new one and try to use the same flue chases or same B vents, it's probably not going to work. It may work. There's always a reason that something does work or doesn't work, but most likely it's not going to work. So what we're going to be looking for when we get in there, if this has been in place for a few years already, then we should be seeing some signs of condensation flowing back down. So you'll see that efflorescence. You'll see some signs of scorching that comes back in there, rust that comes in there. These are all clues that I'm not venting properly. Even with the old natural draft furnaces like we're using this one, if we would put that into an old clay tile lined chimney and the vent connector would go into that, just about every furnace that I've ever seen, I haven't run into one yet, where they say that you could go ahead and put a mid-efficiency into a clay line flue. I haven't seen one model number yet that says that it's okay. So every one of these things should have a flue liner in them. And so instead of discharging into the clay line flue, I should have either a stainless steel or an aluminum corrugated flexible piece of metal that goes into that opening and goes all the way up. And again, when I size it, it should be sized to the appliance. That opening that we're showing up here on the appliance right up above the dot, that is what the manufacturer says should be the vent connector. So in all reality, that's the size it should be. Again, we shouldn't get bigger, we shouldn't get smaller. All right. And this is for mid-efficiency furnaces. Here we're showing two different appliances going into the same chimney. And a lot of this, again, is changing. This is going to be for a natural draft furnace and a water heater. We had enough BTUs to go in there originally. Once we either abandon the water heater or once we go with a higher efficient furnace, we're not dumping as much BTUs in there, and we really should be having a liner. But if this is still the original setup and that's how it was done and that's how it was designed, what we're trying to get out of this slide is the lower BTU is above the higher BTU. So the water heater should enter the chimney higher than the furnace does. The purpose of that is so that it helps create a Venturi effect and keeps all the drafting working. This is a common sense one. We have the vent connector going into the chimney. The bigger pipe is for the furnace. The one above it is for the water heater that goes in there. You can see how the mortar is missing. There's openings that are in there. We don't want to leave a chance for any of those bad gases to come into the house. That needs to be sealed up. You keep these pipes, the bigger pipes, and you start using them on the more high efficiency units. There's a lot of condensation, a lot of moisture. And if I'm not drafting that out, moving it quick and getting it out of the house, it just starts to rust and corrode these pipes. This to me was, again, another obvious defect. We see a big corroded hole in the vent connector that's just spewing carbon monoxide into the house. Nobody was going to argue with this one when we called it out. So when we see the liners inside the flue, the orange pipe that's coming up, that's the clay liner. In our area, it's very common that the round ones were used for the gas appliances. The square ones, which are bigger, were used for wood fireplaces and such. But again, once I put in a higher efficient furnace, so a mid-efficiency forced draft unit, or if I abandon the water heater, again, I don't have, if I had a 100,000 BTU furnace and a 40,000 BTU water heater, and now I put a high efficiency, so I direct vented my furnace, I only have a water heater going up there. Now I only have 40,000 BTUs going up there. That needs to be brought down to the right size. And then from the top, we should be able to see some sort of a metal pipe and a cap to prevent rain from coming in there. That should be installed. Sometimes you'll see a flat piece that goes over the top of the flue, and that keeps the water from coming into it. And then they'll just have a standard B vent opening on top of it. So now we get into the high efficiency furnaces. And each one of these things are different. And you do have to look at the manufacturer's venting instructions, and depending on the size that they're going to be is how long of a run that you could have. Now, when we're dealing with the high efficiency ones, very rarely do I ever see these things have a problem. Those PVCs are pipes. First of all, they're designed to take the corrosion. The fans are usually powerful enough to go ahead and push all the air out. And then they are sloped backwards, not just to let the heat rise, mind you, but more so to let the condensation fall back. And then we end up collecting that condensation and we have to allow it to drain. When we talk about high efficiency furnaces, we should understand that these are also called condensing furnaces. When you talk about using a 95% furnace, all right, realize what we were saying before when we talked about clocking the meters, all right? If this is, and I'm just going to use round numbers to keep the math simple, if this is a 100,000 BTU furnace, that means that fire at the top of this screen up here, this fire is creating 100,000 BTUs. As the heat that's been created from there goes down into the primary and into the secondary heat exchanger, during all this whole process, I'm absorbing 95% of this heat that I'm creating. 95% of that heat is going through the house. Only 5% of that heat is being exhausted. I still have 100% of all the combustion byproducts. So I still have whatever carbon monoxide is being produced, whatever carbon dioxide, however much oxygen is left. That's all still in the bad gases, and that does need to be exhausted to the outside. All right. But since I'm absorbing 95% of the heat, and only 5,000 BTUs are going out the vent, that change in temperature is so drastic that it pulls a lot of moisture and condensation out of the air. Hence, that's why they get the name of a condensing furnace. I have no choice. I have to be able to collect that condensation, and I have to give that condensation a place to drain. In our area, we pretty much go with gravity drains. Typically, there's going to be a floor drain nearby the furnace somewhere. If there isn't, then I'm going to have a condensate pump, and that's what they're well, that's not what they're showing here. It's a neutralizer. We don't use neutralizers in our area so much. We just let it go right into the raw sewage as it comes in there. But it's like when a cold front comes in, we usually get rain associated with it. We get a sudden temperature drop, and then it rains. Same thing here. I change that temperature. I go from, at the beginning of that fire, it's probably going to be about 300-400 degrees where that fire is, probably hotter. And then when I leave, it's going to be somewhere around 125 degrees in that ballpark where it's being exhausted. So it might be all the way up to 1,000 degrees up there. So I'm changing from 1,000 down to 100, eating up 90% of that temperature and bringing it to the inside of the house. Just a side note, and we'll talk about it again with high efficiency furnaces. All the way on the bottom of the floor underneath here, when these things are running, we want to peek underneath there and see if they're dripping. A lot of times we'll get a hole or a crack in the secondary heat exchanger. And since that's the lowest point, that condensation is going to collect there. And if there's an opening, then it's just going to drip straight down to the floor. It's a pretty strong indicator if I have water dripping on the floor that I got a hole in that secondary heat exchanger. All right. Same thing though, we still want to be 1/4 inch per foot vented up and away. But again, it's not so much to let the heat rise as it is to let the condensation fall back. Here's our typical high efficiency 2-pipe system. On this one, I believe we're drawing combustion air in from the top. That's that middle pipe up here. and then we're exhausting combustion air out this way. All right, so the fan is here, and that's blowing the air out there and creating our pressure differentials. We can use this type of furnace and draw combustion air from inside the house. We have to go back to those room sizes and fresh air for the combustion air coming in there. Me personally, I just think it's a waste of time and energy if you're going to go ahead and do that. One of the nice things about these things that makes them 95% efficient as well is I don't use any of the air that I've already conditioned or any of the air that I've already heated to go ahead and make a fire and blow that air to the outside. I'm bringing in outside air, using that to make my fire, and then I just keep my indoor air. If I disconnect that combustion pipe from the outside and I start using inside combustion air, now I'm taking air that I've already heated. I've already paid to heat this air. Now I'm using that to go ahead and make, using it as combustion air, and then I'm just going to exhaust it outside my building. And that has to be brought in and replaced. And where does it come from? It comes from the outside, and now I have to heat that air again. So that reduces the efficiency. I have nothing to back this up, but in my opinion, if you bring combustion air on a high efficiency furnace, it's the same thing as being an 80% furnace. The amount of air that flows through there that you're using for the fire and blowing back outside is, you might as well just buy an 80%er and leave it at that. But that's just my 2 cents. I like to see both pipes being used when you can. Discharging the high efficiency furnaces, we have to keep them away from windows, soffits, anywhere where that carbon monoxide gas could come back into the building. They have to be stayed away from the gas meters, outlets, doorways, walkways, and so forth. Surprisingly, most of our clearances are actually pretty small. We don't have many furnaces that are going to be over 100,000 BTUs. So most of our vent connectors, and it looks bad, but most of them could be within a foot to an openable window. All right. If it's over 100,000 BTUs, then it needs to be further away. Being above the grade, I would always take in snow issues, especially for the combustion air intake. I think the exhaust, it's going to more or less melt everything when it comes out of there, so I'm not too worried about that one. But the air intake, if that's covered with snow and I can't draw combustion air in, then my furnace isn't going to start. They have pressure differential switches in there to keep it safe. Improper, so if we're right next to a window, obviously too close to the ground, below the window, less than a foot, these are all going to be things we want to look for. And again, it's only 12 inches. And so we're talking about the discharge and not the intake. So on these two, we have 2 different furnaces. What's folded downwards, that's my exhaust. And then what's pointed straight outward, that's my, I take that back, I'm sorry. What's pointed straight outward is my exhaust. And what's pointed down, that's my intake. I got those flipped around, it comes in there. So that exhaust, as I'm blowing air away, that's what needs to be a foot away from those windows. And yeah, I think I'm close, but I don't think I'm close enough to where I'd call these out. And the other thing is, when it's new construction like this, typically they're not done wrong. We're going to have a code official, but nonetheless, we're not going to rely on someone else's work. They're paying us to do our work. We should know the rules. 1 foot is our magic number. Now, when I start seeing a whole lot of hokiness that goes on here, not sure what's the water heater, what's a furnace, what's a sump pump discharge. We could probably figure all that out and take pretty good guesses at it. Water heaters are typically going to be bigger. The furnaces are typically going to be paired up, and I'm guessing we have 2 sump discharges here, but just being over that basement window, I would have an issue with that as well. And if this is a sump discharge here, yeah, I don't know if that has enough oompa to get past that window. And then if this is a water heater discharge here, I think I'm blowing that right into that window well, and that would cause it to come into the house. So, yeah, anytime I see stuff that's messy like this, I get a little panicky and a little nervous, and I just start taking pictures and diagramming everything quite a bit better. What we're seeing now is single pipes coming out of walls, but it doesn't look like there's a combustion air pipe, so we're just doing exhaust. And that may be true. It may just be an exhaust only. But in this situation, it's not. All right. If you can see, there's kind of another pipe in there with it. So what happens is they put a pipe in a pipe, and there's special fittings to make that work. So we're exhausting out the middle. I'll go back. All right. So we're exhausting out of here, but then right around the outer rim is where my combustion air is coming into. So even though it's only one pipe, we're still doing both different things. We're bringing combustion air in, and we're exhausting gases out. And how we do that, this is what it looks like on the inside. So this pipe up here is my exhaust, and this one down here is my combustion air intake. Other clues on the outside that this is happening is, and this is what I actually have on my house, you'll see the cone-shaped ones. So the area behind here is where my combustion air is coming in, and then of course my exhaust is coming out of the point here. So I still using both pipes, even though I'm only seeing one on the outside. The flat panels, same thing. Around the outside edges, up here is where we're drawing in our combustion air, and then our exhaust air is going to the outside. When they started bringing in high efficiency furnaces, and there were a lot of condo buildings and these high rises in the city, and they're like, well, everything we have here, we have vent pipes going through the middle. What are we going to do if these things have to be sidewall vented? We don't want to have a whole bunch of pipes sticking out of our building. It's going to look horrible. So they started making things a little bit more attractive, and I don't think these things are too bad looking. And they could be painted. So here's a typical water heater. I have seen them glued. For the most part, though, I usually see a pressure clamp around these things so that'll cinch up on it, and it could be removed when I have to remove the water heater. It just makes life a lot easier in the future. But yes, it can end up being glued. I know I found a video, and I lift up on these things just to see if they are secure in there. I mean, I do have a fan that's being blown on there. If it's loose and not tight around it, then I'm going to roll the dice and take a chance of carbon monoxide being blown into the building. But more so, it's the other way around. I don't want somebody sending me a video of saying, why didn't you tell me that this thing's not connected? So I just lift up on it and make sure the pipes are secure. I know this isn't really about heating, but again, different appliances, we vent them in different ways, and a dryer is an appliance. They do have different types of ducts that could be there. At no time are we allowed to use a plastic duct for a dryer. At least if it does exist, I am definitely not aware of it. All right. I've seen the soft foil types. I've seen the hard foil types. So these are the hard foil ones. Most dryer manufacturers, they call for these hard metal ones, and I've heard a lot of home inspectors. They're kind of adamant about it. They want these hard ones to be there. I've seen the foil type ones, and I don't believe I have a picture of it. I don't. I've seen the foil type ones. I actually don't have a problem with those. So I think I'm in the minority with it. But again, we're all entitled to our own opinions. The foil ones, they are UL listed. All right, so they are tested and proven to work with all the different ones. But most of the dryer manufacturers say that we don't want those foil things on our dryers. So they're the ones that say it's not a good idea. Me personally, I really don't have an issue, and I don't call them out. I actually like them better With these hard ones like this, I've seen people push their dryers back and then they end up smashing the pipe. And once you do that, you got to kind of throw it away and get a new pipe. With those foil ones, if you smash it, you pull it away, it kind of springs back to normal. So that's another thing I like about it. These are a little bit smoother, so they don't collect as much lint inside of them. Where the foil ones, they're kind of corrugated for, far worse, far rougher than what we're seeing here. And they are known for collecting a lot of dryer lint. And if it gets clogged up, the dryers, they just keep pumping along. The only clue you're going to get is that your clothes aren't drying as fast. But, yeah, I don't know what else to tell people. I'm not a fan of cleaning the vent connectors. And you know what? I'm using the term vent connector and I'm using it wrong. These are called transition vents. So, and these are also not allowed to go through the structure or through a floor. Typically, I believe they're 6 feet max in length. And then, but the dryer vents, which are smooth walls, some dryer companies say you can go up to 50 feet on the smooth wall ones, but not with these things. Here we're just showing where it's a small smooth wall line that goes through a wall, and then the transition vent is what connects it from the vent to the appliance. Anyway, I think I babbled enough about that. I'm okay with the foil ones. You're going to have to make your own call on that one. All right. Thermostats, and then basically it's what turns the furnaces or hydronic boilers and so forth. It turns them on and off. It's really nothing more than an automated light switch, for lack of a better term. When the temperature drops down below the desired amount, then the thermostat flips the switch on and the furnace turns on. And the furnace stays on. It keeps running and running and running and running until the thermostat says, okay, I'm warm enough, and then it turns itself off. Nothing more than that. It doesn't adjust the fire, doesn't make the fire burn any hotter or cooler. A furnace does what it does, and that's all it does. All right. Humidistats is basically the same thing, only it uses its humidity sensors to turn the humidifier on and off. So that's also a switch. The isolation or equipment cutoff switch, we should find that within reach of the furnace, and that's so somebody can work on the furnace and turn the power off to it without taking a chance that the automatic thermostat automatically turns the furnace on. Right. So a few basic, I think they're kind of common sense rules. Older thermostats, the ones that had the little mercury bulbs in them, older ones, they need to be level. They need to be straight up and down. I'm not too sure, and I don't believe it's the case, when you start getting into the newer ones, such as the Nest and the Ecobees. Those have different sensors inside of them, and they could probably be put on an angle and still be working fine. But in all reality, everything should be straight up and down. We also want to look at the location of those devices. They shouldn't be in direct sunlight. They shouldn't be having a heat blown on them or air conditioning blowing on them. They shouldn't be near a refrigerator or a stove or any other appliance that's going to be putting off heat. We kind of want them in the center of the area of the heat that we want to control, so not on outside walls or drafts. And if you think about it, why would I want any outside influence on that thermometer to be able to turn this thing on and off? All right. So old school stuff, the old coil thermostats with the mercury bulb in there. And basically, it's a piece of metal that works off of the principle where when something gets hot, it expands. When something gets cold, it shrinks. So if I take that piece of metal and I spin it around like we're seeing here, as it gets cold, it's going to rotate and start to close. And when it does that, the mercury ball is going to slide over and basically close the switch or the contacts on there, and that's going to turn the furnace on. And as the furnace is operating and gets the room warmer and warmer, this thing is going to want to uncoil at that point in time. And when that happens, then the mercury falls away from the contacts, and the furnace is told to shut down. Plain and simple. Just a nice on-off switch. Mercury was found to be bad for human beings, so we started getting rid of it. There it goes. Nowadays, what we're doing is getting into the magnets, and we're getting rid of the mercuries, but it's still the same principle. All right, so that coil comes down, reaches the other magnet. Once it gets close enough, it pulls them together, in which case it pinches or closes the circuit and turns it on. And as it heats up and gets hot, it tries to expand enough where it breaks the circuit and causes everything to close. Sorry about that. Anticipators, they're able to tell how fast the temperature is rising and how long the furnace needs to operate in order to reach that number, so it actually turns the fire off sooner and then later. So getting back a little bit, when the furnace is operating, we have a fire inside the heat exchanger. The heat exchanger is the metal part that keeps all the bad gases, keeps the fire, keeps that contained. The metal gets hot itself, and then we blow air around the metal in order to absorb that heat that's passing through conduction. We absorb that heat and bring it to our rooms. When the fire goes out, that piece of metal is still hot. That's still usable heat. All right. So we're going to keep the blower fan blowing air, absorbing that heat from the metal and bringing that heat into the house. This anticipator anticipates how that's working, and it says, all right, we're going up 1 degree every 5 minutes, and we're going to shut the fire down, and we know that we'll have still 5 more minutes of heat. And of course, I'm making up numbers. But it anticipates and it shuts the fire off early before it reaches the desired temperature, knowing that there's going to be enough heat in the heat exchanger to reach that, and that's all programmed with everything together. Here we're showing a programmable thermostat along with an old humidistat on there. I still run into these old programmables, but nowadays everybody seems to be going with the Nest, or like I said, the Ecobees, and there's a few other ones where they're dialed, and they're different. New technology is always going to come out. The biggest thing that I got, and it sounds dumb, all right, but every time I change a thermostat in somebody's house, I always want to remember where that thing was set at, and I want to change it back to where I found it. My whole goal is not to upset the person who's still living there. We've already done quite a bit of violating of their privacy. We're going into their home and we're giving it a thorough once-over. And me included, it's kind of an uneasy feeling when somebody else is in there judging you and every part of your home that's on there. And it's easy to upset people with this. They're used to certain temperatures in their home, and they want to have those certain temperatures. If I come in there and I raise it up to 80 degrees, and all of a sudden they come home to a house that's 80 degrees, they're not going to be happy with me. The good news is that if they don't come home for a little while, these programmable thermostats still usually go back to their programming. So you don't override them permanently. You just override them till the next setting comes around. But either way, it's just good practice to return that thing back to where you found it. Right. Shut-off switches, like I said, they should be in the same room wherever the furnace is. I kind of like them mounted on the furnace myself. It kind of verifies that the furnace is also grounded, when it's connected to our conduit system and our junction box and so forth that's on there. To me, it's just a smart way to protect it. All right, we're going to start getting into our different types of furnaces. The first one you're expected to recognize is called a gravity furnace. Gravity furnaces did nothing but turn a fire on and turn a fire off. The heat exchangers of these things were thick cast iron. I want to say probably about 1.5 to 2 inches thick, maybe even 3 inches. They were just big and solid. All right. The fire would burn, heat up. It would get that cast iron refractory pot super hot. The circulation air would be on the outside. And as I mentioned earlier, we don't have a blower fan on these, so it worked on the principle of convection with hot air normally rising. So the hot air would start to rise. We would have our registers, our grills, our diffusers, whatever we had, they would be in the middle of the home. So the hot air would have the shortest, straightest distance going up, and then that would start dumping into the rooms. Usually I would have one central return that comes back down on these things, and they're old. I don't know what much more to say. These are typically going to be in houses that were built before World War II. I don't think we were really using these things after World War II, but there is a possibility. But most of them are going to be in homes before World War II. No blower fans, no filters, slow air movement. Principle that hot air rises, cold air falls, creating a convection loop. So the hot air would come up here, and we'll leave through this room here, and then cold air would come back down, get reheated, and basically we're creating a convection loop inside here for a gravity furnace. This is a typical gravity furnace that comes in here. As far as test questions that you might get on a state exam or on a one final, it's kind of the duct sizes that I want you to be aware of. Let me go to the next one. I think that might help. So the returns. So this is a return. Back here is a return. These things are supposed to be 3 times as big as whatever the supplies are. So these are supplies. Typically these are going to be 8-inch ducts that go to the different rooms, and these would be 2-foot returns that come back. Again, no filter, no fan, or nothing else. Over here is going to be my vent connector, and if I follow that, that's going to go to the chimney. We go back to the front of this. If I open up this door right here, I can literally stick my head inside that heat exchanger, all right, and look at the entire inside of it. It will be smaller than what we're looking at here. There is going to be an airspace that runs between the outside jacket and the inside refractory pot. And as that gets hot, again, that's going to create that hot air movement. Hot air naturally wants to rise. And they work. Because these heat exchangers are so old and so thick, chances are good that there's not going to be a crack or a hole in that heat exchanger at all. It's going to be intact, and there's not going to be a good reason that you're going to tell someone to replace it, other than you want to go ahead and increase the efficiency. But the biggest thing with these things is because, as I mentioned, old school, we put the discharges or the supply registers in the middle of the house. Well, new school, we put those on the outside walls, so the outside of the house. And the reason is, and usually by windows and doors, those are going to be our areas where we had the most amount of heat loss. So we're going to want to replace the heat at those locations before we go anywhere else. And then here we're going to have one central return. So usually switching these things out, people do try to put a forced air furnace and use the same ductwork. But for the most part, you're probably going to end up putting new ductwork in there as well. Gravity furnace. Now, I know it says octopus on there, and that's more of a nickname. than anything else. And if you look at the ductwork coming out of the top of this one, the actual piece itself kind of looks like the body of a squid and all the legs that are coming off of it. But the real name I want you to know is gravity furnace. No blower fan, nothing but turn fire on, turn it off. No filter. There's nothing to go ahead and get the circulation in. All right. So here we're going to switch over to forced air furnaces. And this is actually a oil furnace. So anytime I get that blow dryer looking object in any diagram, that's pretty much an oil burner that we're looking at. And if I come up here to the right side, right above the dot there, you could see that's our barometric damper that we talked about earlier. All right. Now, airflow into forced air furnaces is important. All right. And it should always be the same way. Now, they're showing this where it almost looks like the vent or the vent connector is going through the return air. Yeah, there was a very short time frame where that happened, but we don't do that anymore. Pressure differentials are very important in the safety of how these heating units work. All right. So first thing we want to do is talk about the airflow. So the return air comes in. The first thing we're going to do is filter that air. All right. After we filter that air, then we're going to pressurize that air. So right now, here's our blower fan. So filter, fan. Then we're going to go to our heat exchanger. And then last but not least, if I had an air conditioning system, and this one doesn't show it, if I had an air conditioning system, the air conditioning system would be last. So filter, fan, heat exchanger, air conditioning system. Now, if I had the fan running down here, that fan on this side of the fan, the filter side, is going to be under a negative pressure. After the fan, it's going to be under a positive pressure. If I ran this pipe through the negative pressure and I had a hole or a crack or something where we saw that rust corroding it, I'm actually going to be creating a vacuum and pulling the bad gases and the carbon monoxide into my circulation air. So we don't want to have any sort of venting running through a low pressure zone like any ductwork that's going to be before my blower fan. All right. And then if we think about it, even if I had a hole in my heat exchanger, because now if this is under zero pressure, because I do not have an inducer fan, if I had an inducer fan, I would create a negative pressure inside here. And then I would also have a positive pressure being created on the outside of the heat exchanger. If I did have a hole or crack or opening in there, that means that the air would be flowing into the heat exchanger instead of allowing gases to escape. Please don't take what I just said as me saying that it's okay to have a hole or a crack in the heat exchanger. It is not, by any means. All I'm saying is the design of these furnaces, we have multiple different safety features that are put into these things. So the first one is going to be our fuel air mixture. If that oil burner is doing what it's supposed to be doing, or my gas burners or propane burners are tuned right, I'm going to produce very low levels of carbon monoxide. The carbon monoxide is what's going to harm a human being. All right, so that's safety feature number one. The heat exchanger itself, if that's intact and there's no cracks, openings, or anything else in there, then there's no way for those bad gases to pass over and get into my circulation air. Safety feature number two. And then the third one is going to be my air pressure differentials. I have to have my blower fan before that heat exchanger because I want to create a positive pressure on the outside of that heat exchanger so that if I did have any openings, I'm going to lower or reduce the risk of carbon monoxide getting into my circulation air and then hence coming into my house. All right. So new school, we put our radiators under the windows and we bring our return air from the outside. And then you'll see on just about every other slide that we show for forced air furnaces, it's going to be filter fan, heat exchanger, air conditioner. All right. Airflow and ductworks. This is another complaint call if you don't take the time to check. You will run into houses that A, don't even have a heat source in a room. We've run into that a few times. B, they're going to be at very odd locations, like right in the middle of the ceiling someplace, and it was added afterwards. Or you just get a real cruddy flow coming out of it. So our shortcut method is to take the thermal imager around and we shine it on all the openings where the exhausts are coming out of there. And the furnace was running for about 5-10 minutes already. I would not only want to see that the grill itself is warm, but if it's close to the wall, I actually like to see flame patterns on the wall so that I know heat is hitting that and it's coming out of there. All right. Same thing for the ceilings and so forth. If I see just warm air, I typically go over the area and I just use my sock. I take my shoes off in most homes. Otherwise, I use the back of my hand. I think it's called an anemometer, which checks for airflow. I know some people will put that on there. There's nothing wrong with it. I think I'm a big fan about more data, more definitive answers when we do our test. So if I want to say that I have slow airflow coming out of one ductwork, and I could show that I have 40 cubic feet from this one, 35 from that one, 41 from this one, 38 from this one, and 4 from this one here, and I could show numbers on each one of them, I think that really sends the message home that I have low airflow coming out of this one for my clients in case they want to negotiate these things. So the shapes, the more round they are, the easier air is to flow, the distance and size of the ductwork matters, the smoothness inside. We find those corrugated loop ones sometimes in attics. It's not very common in the Chicago area, but it's getting to be more and more common. So the rougher they are, the bigger the chance to reduce the airflow, the bigger the pipes that they need to be. Hot air does move easier through ductwork than cold air. So not only do we have to size the ductwork for the heat, but we also have to size it for the air conditioning. Typically, most furnace fans, they're going to blow at a higher speed when it's running in air conditioning mode because we know cold air is harder to push through the ductwork. So the fan will make up that weakness that it needs. All right. And obviously, keeping a furnace in the middle is always going to be the best thing we can do. I would like you to be able to recognize the difference between a register, a grill, and a diffuser. All right. So a register is going to have a damper on it. Typically, we'll find these in the floors and the walls and also in the ceilings. Grills are basically the same thing as a damper, but they're the same thing as a register, but there is no damper on them. All right. Where diffusers, it has different angles. So basically, it kind of spreads the air out more throughout the room. Typically, we're going to find those in ceilings. We really don't find them in floors and walls. But up in the attic spots, you're going to find diffusers. Registers, they have dampers. Grills do not. Diffusers are going to be typically in the ceiling. Registers are typically going to be on supplies. Grills are going to be typically on returns. And diffusers are going to be typically on supplies. So when we're blowing air into a room, sometimes we're going to run into ductwork or return ducts where there'll be a register and a grill. So typically they'll have a grill on top and a register on the bottom. To use these things to the fullest advantage, we want to realize what we're trying to do to the room and remove what we're not trying to do to the room, if that makes sense. So in other words, they're showing the top drawing being in cooling mode, so in the summer, so the air conditioning is running, all right? So if I want to add cool air to the room, that means I want to remove hot air from the room. So the hot air is always going to be higher, so I want to remove air from the top. So the bottom grill, the bottom register, I'm going to close that register, close that damper. And that way air won't flow in through there, and it's going to pull all the air from the top where it's warm. And we're going to pull that down to get reconditioned. The bottom illustration in the winter mode, what they did is they opened up that damper that blocks the grill above it. And so we're going to be pulling in the cool air. Cool air is found down low. We'll be pulling that into the house. Not all homes have this, but if you do happen to do an inspection on a house that does have this, you should be able to explain to your client why it's there, how to work it, and how to make it the most efficient. So as we're showing on this drawing here, the grill is on top, the register is on the bottom. When it's in heat mode or the furnace is running heat, we want that register on the bottom open, so the damper open. And when we're running in air conditioning mode, we want to take it from the top, so we close the damper. We're going to run into houses also that have a central return still. Most of the time that's where we're going to find our filter when we do have that central return. So we want to show our clients how to open it and change it. If they know already, that's great. If they don't, they're going to want to learn. All right. We also need to make sure that the air can flow in and out of that room with ease. All right. Not only when the door is open, but when the door is closed. So these things are designed to be where there's an undercut, I guess, under that door, so that as I'm blowing air in, I can let the air get out. If I have carpeting or that opening's too small, that's going to restrict the amount of airflow that's coming out of there. I've seen where they'll put grills up in the ceiling as well. I think that's a great idea, something that permanently lets it get out of there. One test that I do, and very rarely, but I have found them, where these things are problems, I make sure all the bedroom doors are closed inside, and I'll go into each bedroom door and I'll open it with the furnace running, or the air conditioning running, just as long as there's airflow coming through there. And then I'm going to push that door closed, and I'm going to push it slowly closed. And if I get towards the end and it pulls away and kind of slams shut, that's a no-brainer. I mean, something's restricting the airflow out of there. It wants to flow, and we need to let it flow, all right? And so either we undercut the door more, or we have to put in another vent or something in order to let that air get through there. Again, our filters, I can't stress enough to my clients the importance of keeping these air filters clean, keeping them changed. People always ask, how often should we do it? And to me, it depends on the filter. I know they have some of them that you could keep in there for a year, and they have other ones that you should be changing every 30 days. All right. I think it matters more so how much air you're flowing, how clean your house is, pets. There's a lot of other things that come into play. But the main purpose of these filters is to filter the air. But when they get dirty, they also restrict the airflow that comes across. One of the numbers or one of the measurements I'm hoping you're going to be taking in your system is what we call the delta T, or the temperature change going across the heat exchanger. So it's what they refer to as the temperature rise. We'll find that number on the data plates inside the furnaces. Typically, they're going to be a 30-degree range, all right? And I've seen them anywhere from 25 to 55, all the way up to 55 to 85 degrees, all right? And I'm sure it would be even more than that, but those are pretty much the ranges that I see. So what that means is if I got a 70-degree temperature in the house and I got a 30 to 60 temperature rise, that means I should be between 100 and 130 degrees. So I'm going to take one of those dial thermometers or turkey thermometers or whatever other device I have. I'm going to measure either the air where the filter is, which is pretty much the room air, and you could see that on your thermostat. And then I'm going to go above the plenum and measure that temperature there as well. And if I'm too high, I like to remove the filter and see if that lowers that temperature back down to normal. Because if that filter is restricting the airflow and now my circulation air is slowed down coming across that, it's going to absorb a lot more heat. And that actually shortens the lifespan of these furnaces. because those metals and that heat exchanger, everything, when it gets hot, it expands. When it gets cold, it shrinks. And they're only designed to work on a certain temperature rise, all right? If I start overheating them or overcooling them, then that shortens their lifespan. We don't want to leave it like that. So making sure we're within that range is kind of a big deal to me. All right. Here they ran some ductwork through the garage, and they actually have a diffuser up in the ceiling of the garage. Sounds great. Now I got a heated garage, so everything's good. But we're going to talk about this, if I do an exterior one, which I think I will. We're going to end up talking about breaching of the firewall. So if I have an opening with ductwork that comes back into the house, if there's any gas fumes that's coming from the garage, or God forbid there's a fire, that just makes it an easy way coming in there. Same thing with the ductwork. Now I can run ductwork through a garage. That's not a problem. But it does have to be in a soffit. It does have to be protected by drywall. Just being out in the open isn't a good idea. There was a time frame when that wasn't considered a problem. And houses that were built after World War II, they used that garage space to get heat to different rooms. But I don't know when it changed and all. But in today's day, new construction, and even if I saw that, I would still say it's not a good idea, and I would do what I can to encourage somebody to get some sort of drywall or something wrapped around it at all, just to make it a little more airtight. All right. Older blower fans, belt-driven ones, I would encourage my client to get a belt and leave it on the ground there. Those things break at the worst times. But again, if I start seeing these older things nowadays, I would have to warn my client that this is just an older unit and it will fail eventually, and they're going to be getting an upgrade as that comes along. Everything now, these blower fans, they're all direct drive, so the motors are actually built into the fan, so we don't use belts anymore where it comes to it. And they're also multi-speed ones, or adjustable speeds. So you can actually program them on the computer by how much air it forces through the ductwork. And as I said earlier, cold air, harder to push, more fan speed. These belt-driven ones, they were one speed only. So when we start getting into our forced air furnaces now, we need to start learning the different parts that we're going to be finding inside the furnace. All right. I talk about that temperature rise that we measure with those turkey thermometers or little dial thermometers, and this area up here, the ductwork that would be there, that would be called the plenum, and this is the area that I usually take that measurements. So when I'm talking about a 30 to 60 degree temperature rise, if we come in here at 70, this is where my heat exchanger is going to be. That's where I'm going to add heat to it. And then above the heat exchanger in my plenum, that's where I want to be at that 100 to 130 degree mark. All right. Now, if this blower fan fails, and because that fire is going to be lit, that fire is going to be constantly adding BTUs to the metal of the heat exchanger. So it's going to keep getting hotter and hotter and hotter. This furnace is engineered that as many BTUs as I'm adding through the fire here, I'm going to be removing those BTUs with the blower fan that I'm circulating air through the house. All right. So if that blower fan fails, whether the motor seizes up, comes loose, something blocks it, the wires come disconnected, whatever, I'm not able to remove the BTUs. So this furnace is going to get hotter and hotter and hotter. That's what this high limit switch or fan switch does. All right. Older units, this was a dial type machine on here, and it would have that same coil that we saw with the thermostats on there. And this is actually what turned the fan on and off back in the day. All right. So when the furnace would kick on, the burners would ignite and they would start heating up the heat exchanger. And the fan wouldn't kick on right away because the air around the heat exchanger is still cold. And we don't want to circulate cold air. We want to wait till it gets warm. So that would wait till somewhere around like 140 degrees. All right. At 140 degrees, this probe would flip a switch and say, okay, blower fan, you get turned on. All right. But again, let's say that blower fan was broken and it didn't operate. Then it would keep getting hotter and hotter and hotter until it reached somewhere around 170, 180 degrees. At that point in time, it's too hot, and that would actually turn the fire off and shut down the whole furnace and let everything cool back down again so that it didn't burn the house down, or start on fire itself. But let's say it was working, the blower fan was removing the heat, I'm staying within that safety zone, I didn't reach the high limit on there, then what happens is my thermostat is satisfied. The thermostat says, okay, it's enough, you can shut down. We may mention before that the heat exchanger is still hot, even though the fire is not there anymore, so we're still going to use that air. Using that air basically is what this fan limit switch does. So it's going to let that fan run until it gets down to somewhere around 100 degrees, plus or minus. And then once it gets there, it knows that there's no more usable heat, and then it shuts the blower fan off. All right. Sorry about that. Okay. So fan on, 140. Fan off, 100. Furnace shutdown, 200 is a nice easy number to remember. All right. You can adjust that. All right. And I've never run into this where this thing was set off that much. I do pull that cover off. I do check those numbers if I see an old furnace like this, just to make sure it's not there. But if somebody has this thing set up to 350 degrees just to keep that thing going, that's not a good thing. All right. They can go, they're really turning it into a gravity furnace, but the amount of heat that's there is not going to be a positive thing. So there's an actual picture of what it looks like, and that's what is circled right in here. Typically, it's going to be between two of the heat exchangers. So if I go down on the bottom, that's where the burners are. That has its own heat exchanger coming up here. That's another heat exchanger and another heat exchanger and so forth. The air is going to flow between the two heat exchangers, and that's where we're going to find this temperature sensor that's going to be in the circulation air, the air that we breathe. All right. Nowadays, with the newer furnaces, and this is pretty much what we're all going to be running into, it's more of a high limit than anything else. So it'll send a signal to the furnace when it gets too hot for the furnace to shut down. The manufacturers of these furnaces and the engineers that went ahead and put all these things together, they know, how long it takes before I heat up my heat exchanger. All right, so whether it's 20 seconds, 10 seconds, 30 seconds, they're going to let the computer now decide, we're going to light the flame, we're going to make sure that the flame is lit, we're going to make sure we're getting some heat and the temperature is rising. So we're confirming that our flame is there, and then we're going to let it go for about 15 seconds, and then we're going to kick on our blower fan. If my blower fan doesn't work and I reach a certain temperature, then the fan limit switch or the high temperature sensor is going to activate and it's going to shut our furnace down. All right. I do expect you to be able, if I had you in front of me with the furnace, on any furnace, to be able to identify the fan limit switch or the high limit sensor on any furnace. Newer units, it's going to be just a rectangular. Sometimes they're black, sometimes they're brown, sometimes they're gray. Older units, they're going to be a dial-up thing. Typically, there's going to be that silver box that's on top of it. That silver box was removed so we could see the inner components of this one here. All right, but most of the time, that's what we're going to run into. All right, different types of drafts. I would like you to know the difference between a natural draft, an induced draft, and a forced draft. All right. The left-hand side. All right. So this furnace over here. Notice there's no inducer fan. So the middle one we have an inducer fan. The right one we have an inducer fan. But the left one we don't. All right. So this one, we're going to create a fire at the bottom of the heat exchanger. That heat is naturally going to rise, and that's going to go through my vent connector into my chimney or B-vent or whatever and leave the building. All right. Hot air naturally rises. That's considered a natural draft. There's no mechanical support whatsoever. This second one here is a forced draft. Now we have the same fan that's there. Now that fan is taking air, so our combustion air is coming from the outside. This is going to be under a negative pressure here. And then I'm blowing air into the heat exchanger. So I'm forcing my draft into the heat exchanger. Now I'm going to have a positive pressure inside this heat exchanger. All right. The reason we don't do this anymore is when the furnace is starting up and I have a fire going inside, if that is pressurized on the inside, and if there's a hole anywhere on the inside, then I'm going to end up with pushing those combustion gases or the after-fire gases or the carbon monoxide into my circulation air. And depending on how big that opening is and where that opening is, that may happen after the blower fan is kicked on. It will most likely happen before the blower fan kicks on. But if the blower fan is before the heat exchanger, and that creates a positive pressure on the outside and a positive pressure on the inside, whichever fan is stronger is going to cause the air movement to come in there. But if it's at the very top, sometimes it actually creates a Venturi effect as well. All right. So we're really not going to run into too many furnaces that are forced draft. That's going to be on the very early stages of the higher efficiency furnaces. They realized this was a mistake. They realized that this was dangerous. As soon as those heat exchangers failed, then that carbon monoxide was going into the rooms and people could definitely get injured, killed, or whatever. It gets bad. All right. So we don't do that anymore. Nowadays, what we do is what we call induced draft. All right. So on the third one, or the far right one, we're looking at our inducer fan here. That when that's running, it actually creates a negative pressure inside the heat exchanger. It creates a positive pressure afterwards. So now, even though it's a smaller fan and not as powerful as our blower fan, when that burner kicks on and the inducer is going and it creates a negative pressure in there, at least if there is an opening, we're going to have that secondary safety thing where air is going to come into the heat exchanger and not into the circulation air. And then if I have a positive pressure when the blower fan's going, that even makes it stronger of a pressure differential. So the less likely of a chance that comes in there. And again, me saying that, doesn't mean that a crack or a hole in the heat exchanger is okay because we have these pressure differentials. No, it's still not okay. All right. But I just want you to know some of the engineering that was built into these furnaces that makes it safe. So natural draft, forced draft, induced draft from left to right. Natural draft, forced draft, induced draft. Flues, most of the stuff we're going to be dealing with are going to be category 1, 3, and 4. I never really saw a category 2 furnace. That would be a high efficiency furnace or a condensing furnace that either does not have an inducer fan or it has a forced draft fan when we're dealing with it. So I've never really seen one. So most natural draft furnaces, those are going to be category 1 furnaces. Once we put that inducer fan on it, and so we have a blower fan going, and we're going to be creating a pressure difference inside of it, that's what makes the difference between a category 3 and 4. So in other words, 80%ers are pretty much category 3. 90%ers are category 4 furnaces. Plain and simple. This is a natural draft furnace. What are we looking at here? Atmospheric. Burners do not rely on a fan to push the combustion air. Hot air rises. We kind of chatted about that already. So I'm going to move on to the next one. Checking the heat exchanger. As I was saying on the older natural draft furnaces, It was doable. It was difficult, but it is doable. And there's a lot of other tools that we can use nowadays, and you got to decide um, how deep you want to go into your inspections. All right. And whatever you do, don't be convinced by anybody telling you that it's beyond the standards, above the standards. Our standards of practice that we do is what is written in the IDFPR law in the state of Illinois. So it says we inspect the furnace. We describe it by its fuel source and distinguished characteristics that come in it. But it doesn't say what tools we have to use. It doesn't say how we inspect it or how deep you want to go. None of that. There's many people that will just turn it on and they look at the flame and they say, well, that's a pretty blue flame. And it's and you got heat coming out of it, so I guess it's okay. And they leave it at that. There's other people that put, more expensive equipment on furnaces to check the gases and make sure that everything's tuned right and coming out of there. So you can go everything from a heating contractor to a guy that turns the thermostat on and says, yep, it's making heat. All right, plain and simple. Part of this pressure differentials, all right, I want you to remember, if you think that using a carbon monoxide detector in the circulation air is going to tell you if there's a crack or a hole in the heat exchanger, I'm going to try and convince you that it won't. Okay, I mean, if it's really bad, then it will. If it's so bad that we're getting carbon monoxide leaking into the house, then hopefully you'll be picking it up that way. But small openings, small cracks, which are still dangerous, they're not going to bleed over into the circulation there because of those pressure differentials. All right, but it's still a dangerous seal. So here's a natural draft one. You can see inside of it, it's rusty, it's dirty. I do have another friend of mine who has a very successful business, and he shared with me that he wants all of his guys to, give some sort of a reason. He knows that if you look hard enough at these furnaces, that they are not perfect by any which way, you can identify a reason to get a heating contractor out there and let them do a more thorough inspection. I think that's a very safe, sound advice. I always wanted to be that guy that's able to give you that more thorough inspection. So go from there. Another natural draft furnace. Everything's open on the inside of this thing. I got nothing much more to share. You can see all the rust and corrosion. And same thing going back to this one. You can see how rusty everything is on the inside. But these old natural draft ones weren't, they're just old. They're just in bad shape. I don't know what much more to say. At this point in time, even if it isn't running safe, I still want my client preparing for a new furnace. All right. So the biggest problem with gas forced air furnace, and the biggest thing that they want us there for, is a crack or a hole in the heat exchanger. And more specifically, if there's a chance that carbon monoxide is getting into the circulation air, which could harm somebody. All right. So there are different methods. There's different things that we could do that are evasive and non-evasive. One of the things people can do is put a carbon monoxide detector. I kind of talked a little bit about this in the circulation air that we breathe. But a crack like this one and the pressure differentials, that probably won't show. Same thing with, let me back up a slide here. Smoke candles, this is something I really don't recommend that you do. But you can actually put a lot of smoke inside the heat exchanger. And if there is an opening in there, that smoke will pass through the heat exchanger as long as the blower fan's not running. And then that smoke might be coming into the house. But, this is somebody else's home. And I'm not a big fan of putting that in there. The magic spray is kind of a joke a little bit, but it is an actual spray. I'm going to show a picture of it because I can't think of the name of it beforehand. But it has a lot of alcohol into it, and it is very flammable. And I've seen it work where it actually showed a hole or a crack in the heat exchanger. So with this spray, with the furnace running and the burner going, you actually put the spray into the blower fan of the circulation air. And when you spray it in there, like I said, it's very alcohol based, so it dissipates quickly. But as it goes over the heat exchanger, if there's any openings in that, then that heat, it's going to blow to the inside of that heat exchanger. And if it's able to touch the flame, then it changes the flame from a blue to either a orange or a bright red. And it's pretty cool when you see it happen. So you spray like 6 pumps in there, and yeah, it goes into the flame. The flame goes from blue to red, and then it goes back blue again. The only way for that mist to get there is if it's for that mist to get there is if we have a hole or an opening into that heat exchanger. So, and then the other one out here says flame dance. That one I'm not too comfortable with. I mean, you really have to have a big blast of air from that circulation fan blowing on the flame and causing it to flicker and move. It just doesn't happen. So I wouldn't count on that one. All right, so this is an actual crack in the heat exchanger. We're actually looking at 3 dangers. Even though that crack looks really small, when it heats up, the crack opens up. And then where it is, it's going to lower in or up. All right. This one's kind of a no-brainer. If you can't see it, it's down here at the bottom. This, I didn't make a good circle, but that opening down there is rusted through. But even this rust that I see on here, that would be enough for me to say, hey, listen, you got to get somebody else out here. Chances are good this thing's going to be bad. Or you got to use more definitive equipment to see if anything's bad on here. But as long as we could visibly see it, then we know that there's a hole or crack in it. Another heat exchanger, the entire back of it was blown off. And that's a very common. If you notice when I go back straight to the rear of the heat exchanger is probably one of the most common places that they crack or break. We saw it on all 3 of these actually. And then right where the burners come in, right up underneath it, as it comes back, there's a lot of bends in there and high flame impingement in there. I shouldn't say impingement, but there's high heat in there. And those are other areas that crack and get damaged quickly. All right. So carbon monoxide is serious stuff. It doesn't take all that much. When we're measuring these things, we're measuring in parts per million. All right. So when we got 200 parts per million, that's a lot of parts for where it comes into it. So at 200, well, actually 40, we'll get down there. That's usually when the carbon monoxide alarms start going off. And then I think that's also what they call the threshold limit value, the TLV. And that is the amount of carbon monoxide that the EPA has determined to be safe if you're in a working environment. So you could be there 5 days a week, 8 hours a day in that environment. Anything more than that is dangerous. All right. I still think 40 is dangerous. We shouldn't have anything coming over into the circulation air. All right. So here's another natural draft furnace, straight up vent connector. We have a chimney on the other side of that foundation. All in all, everything looks pretty decent. Our vent connector clearance to combustible is going to be 6 inches. The only thing that I see in this picture that has combustible material that's close is going to be my insulation from my air conditioning line set, my drain from my air conditioning condensate drain, that's PVC, and that's really about it. And both of those, I believe, are 6 inches away. This one here, I got a flexible drain. I do believe that's less than 6 inches away. And even if there is no burning, scorching, or anything on there, I'm going to go ahead and start calling that one out too. Another natural draft furnace. So now we have an inducer fan. And one of the questions I get is when they talk about the vents and the vent connectors, sometimes they're metal, sometimes they're PVC. How do I know when it's a high efficiency? What are my clues? How do I know it needs to be plastic? Or how do I know it needs to be metal? And we cannot mix the two of them, all right? And everything goes to the housing, and I'll show you a closer up picture of it in a little bit. But everything goes to the housing of the inducer fan. If the housing of the fan is plastic, then my vent and vent connector need to be plastic. If the housing of my inducer fan is metal, then my vent connector and my vent need to be metal. Plain and simple. All right. And I'll open that up and see. So on this drawing here, this is my inducer fan. But behind this metal plate, you could see this here is all metal. All right. So when this housing around here is metal, that means that my vent connectors and my vents also have to be metal. This is a mid efficiency or an 80% furnace. And that's going to be my one telltale sign that they're just not going to change. All right. So first thing that happens, thermostat calls for heat. We want to turn it on. Then the computer basically checks all of its quick circuits, make sure it's okay. And the first thing the computer activates that we're going to see operating is going to be this inducer fan. So that wheel is going to start spinning. All right. Now the computer doesn't know if the wheel is actually creating a draft or working at all, or the wires are broken, or it could be, I've seen birds stuck in these things and they didn't operate either. So if it's working and it's going to be creating differences in pressures, we're actually going to sense for that. So this cylinder device right here is called a pressure differential switch. Now sometimes you will see a tube, either it'll go to the heat exchanger or it'll go to the underside of the inducer fan. And if it's spinning, if it's creating those pressures, then that device will close, sending a signal to the computer saying, yep, my inducer fan is running, it's spinning, I created a draft, you're good to go to the next stages. All right. I do expect you to identify the inducer fan. I'm also going to go back and review a couple things. I'm also expecting you to identify this brown disc down here. And I'm hoping you're thinking that's the high limit switch that comes in there. So right now, we should be able to recognize our inducer fan, our pressure differential switch, and our high limit switch. And I don't care if you call it a fan limit switch as well. Either way is fine. All right, here's our typical, again, mid-efficiency furnace. So my inducer housing fan is made of metal, and my vent connector is also made of metal. Now, if you notice that down here, and this is a typical thing that we see, the vent connector, where it enters the furnace, it shrinks down in size. This furnace was changed out. They put a new one in there. It was more efficient than the old natural draft furnace that was there. So it does send up less BTUs than what's going up on there. These vent connectors and vents are supposed to be sized to this appliance, not to the old one. All right. So whether or not this is going to continue to work, I can't say. All right. But I am going to be looking for signs of condensation on all of these joints. Any sort of dripping or anything that's going to show where I have any sort of bad drafting, and I'm going to be aggressive with it. Right, this is the gas. We do have gas pipes here on the left coming in here. And so we know we have to have a 6-inch clearance to our single wall pipe that goes up in here. And this orange hose that we're looking there, that's what connects my inducer fan to that pressure differential switch. And as long as that fan's spinning, I'll be able to create a positive pressure, and this switch will sense it. Now we get up here and we start seeing that rust stains and the white condensation come back in here. You could actually see some dripping on the very bottom underneath here as well. All right. And so it's actually leaking out of the inducer fan. All that condensation's coming back. This furnace is not venting properly. All right. I should not have that condensation coming in here. And I don't want to take ownership of this problem. We're going to document this and we're going to push this off to a heating contractor. Same thing, more corrosion, more rust, more dripping. These are all things that we're going to be pushing off to a heating contractor. Sealed combustion units, we're getting into more of a higher efficient furnace when we come to it. Sometimes the only thing you can see on the inside of these things is through that little peephole right in there. So you're just limited on what you could do. All right. Now these plastic or the high efficiency units, that sizing of the vent connectors, they can get bigger or smaller. So that sizing to the appliance is only for the mid efficiency furnaces, not necessarily for these. But we still want to make sure, no, there's not much we can do because they are going to condensate. Liquid is going to come back. They are going to collect it and they are going to drain it. That's what they're for. So I may mention before about bringing combustion air from the inside. So this high efficiency furnace can operate this way if I'm in a wide open basement. Can't be in a bedroom, can't be in a bathroom, can't draw that combustion air from the bedroom or the bathroom. It needs to be big enough, depending on the BTUs that are there, to get enough combustion air. And quite frankly, now I'm taking conditioned air and bringing that to the outside. Let's see what this is here. So any metal vent, not just mid efficiency. Mark, I don't understand what you're asking me there. And maybe I'm going to wait and hopefully you can give me a clearer question when we come to it and I will address it. Another high efficiency. All right, this way our combustion air is coming from the inside. It's coming from the right-hand side and exhausting to the left. 2 pipes. Again, it is okay to bring combustion air from the inside. We just can't bring it from a bedroom or a bathroom. And the reason for the bathrooms is for the moisture. And from the bedrooms, I think they're afraid of backdrafting and combustion air coming in there. All right. I do want you to know the term backdrafting. I think I used flame rollout already. I've used scorching already. Size changes should be avoided. I'm going to bring that back up here again. Thank you for rewriting that. All right, so size changes should be avoided for any metal venting to avoid corrosion. Exactly, that's the point I was trying to make. Yeah, because anything where we're going to go ahead and collect that condensation, if we don't get a good draft coming out of there, it should be smooth. The only time we're going to have a size change is if we add another appliance to it. So if I go from 1 furnace to 2 furnaces or 1 furnace to a furnace and a water heater, then it will get bigger, all right? But that should be the only time, you know. Otherwise, it will go ahead and reduce it. Alrighty. So backdrafting. On natural draft furnaces, typically on induced draft furnaces, we're not going to have any sort of backdrafting issues. It's just not going to happen. The fans themselves are going to go ahead and make sure that everything gets out of there. If I can't build up the pressure and I can't get the airflow, hopefully the sensors are happening. So it's not impossible that it'll happen, but the chances are very slim that it could happen. Backdrafting is mostly going to be found on natural draft furnaces. All right. So here we have our burners. This is where our combustion air goes in. Our dilution air comes in at the draft hood. So our flame goes in here. We create our bad gases inside the heat exchangers. They group up again and send those bad gases up and out the vent. I have to mix dilution air in with it in order to clean it up, basically, or cool the temperature down so it doesn't move too fast. If there's a blockage in this vent connector, if it has a thermal barrier somewhere in the chimney, then I'm going to start backdrafting. Now with these, I am going to tell you that backdrafting is normal. All right. When they first start up, you are going to backdraft until it gets built up enough heat to get that draft and get it started. You are going to have some, but if it's over a minute and it's still backdrafting or continuously backdrafting, that shouldn't be happening. All right. A little bit in the beginning for a short period of time, that's actually normal. All right. But if it goes on for a long time, that's not normal where it comes with it. Different ways that we could check for backdrafting. Those of us that wear glasses, I usually take the glasses and I'll put it in front of the hood, and if it steams up, it's backdrafting. I've seen where you could take a flashlight and shine the flashlight on an angle on the beam, and then you give a quick blow of air and get the dust up in the air, and you should be able to see that dust going up the vent connector instead of coming down and into the room. Those are also another signs of backdrafting. Typically, you're going to end up seeing rust, and I know I got a picture, rust and scorching on the draft hood here. So just different clues where it comes with it. All right. This is an old natural draft furnace, and you could see the big orange scorching that's right there. This thing has been backdrafting for a long, long time, and all the moisture that comes from the fire has been causing that. I don't know what much more to say. To this is a no-brainer. We actually have scorching on top of the burner draft hood itself, so you can see where not only was it coming out of there, but it was also flowing upwards as well. Just a closer picture of everything. So what we started doing for safety features is they started putting backdraft sensors on these things. And they're nothing more than heat sensors, all right? This is an aftermarket one on a hydronic boiler that's on there. And so that if the heat is coming down and in, that this is going to sense that heat and it's going to shut our boiler off, all right? We actually started putting these on the furnaces as well, so you can see where that little arrow is pointing at. That's going to sense for the backdrafting and again shut everything down. And there's a close-up of that. Nothing more than a heat sensor on there. High efficiency units and where they start and how they absorb the heat. Typically there's going to be two heat exchangers on these. One is going to be our primary heat exchanger, and that's going to be this looping one. Sorry about that. And that's going to be the pipe that comes down this way. This is going to be our primary heat exchanger. Then it goes into a radiator coil, so it's a much narrower tubing, kind of like an air conditioning coil that goes on there. And that's going to be absorbing the secondary one. Now, all the condensation that's going to be created in here, because these are condensing furnaces, so they are going to be creating water or condensation, that's going to settle down here. And if it can't drain out, it's going to actually very corrosive. I forgot if it's alkalytic or acidic, nor does it really matter. It's going to start corroding the heat exchanger, and then we're going to start getting drips coming down to the floor. All right. Yeah, it's looking on the floor when these things are running, see if it's wet. Just a telltale sign. So as the air runs up where the blower fan is, that's going to be room temperature. It's going to absorb most of its heat through the secondary heat exchanger. And then as it gets up higher and higher and higher through the primary heat exchanger, those pipes are going to get hotter. So then as the temperatures equalize out, that's how it absorbs. That's how it absorbs as much heat as it does. And that's what this drawing here is trying to show. So it's colder here on the outside and everything starts getting warmer. It's hottest here and it starts losing the heat as it gets colder, and basically how a high efficiency can be so efficient. Things that we want to look for. All right, we know we're going to create a lot of condensation, so we need to collect and drain that condensation properly. You're going to find that a few different areas where they collected, those things do crack, whether it's from temperature changes or whatever, so because of which they leak. Look for the water, look for the rust, look for all the problems where the tubes are disconnected. We don't use neutralizers in our area. I've never run into one anyway, and it should go into the floor drain. If there's some reason in your area that you become aware that you do have to use a neutralizer, that's what the tank is for on the bottom. I don't know what you would put in there and how often you would have to put it in there, but just know what it is, all right? Temperature rises to me are the most important thing that you could do, all right? So taking that thermostat or thermometer, dial thermometer, turkey thermometer, whatever, and getting that temperature rise and making sure that it matches the data plate, that's huge. All of our vents, our plastic pipes that are connected, everything should be tight and secure. I shouldn't have any stains that are coming out of these things. If it's orange or yellowish in any which way, that usually means that something is leaking out of that pipe. So they are supposed to be sealed airtight and watertight. No water, no air should expel from these. Heat switches, so they do have high limit switches on there. Pressure differentials we talked about. And then the blower door interlock. So just about every door or every furnace that has a blower fan should have an interlock switch on them. I have seen them bypassed quite often. There's a lot of heating contractors that will just put tape on it to bypass it. That way, if the door comes loose, it doesn't shut itself down and people don't get a service call. I get it, and makes sense. But I am not a fan of bypassing any safety device whatsoever. In our line of work, it's the calls that you get were, why didn't you tell me? They all begin with the same magic words. Why didn't you tell me this? All right. And the real truthful answer is because I really didn't think it was that big of a deal, but it's not up to me. It's up to my clients. So I could let them know what it is. I could let them know the rationale behind it and let them make their own decisions when it comes to it. I'm not a believer in trying to convince someone to take the tape off. I want to let them know the argument that the person put it on there, because sometimes the doors aren't sitting tight and that the furnace will shut down and you're not going to know why it shut down. You're going to call the heating person and you're going to be upset that there's a $150 or $250 service call just because the door was loose and you didn't recognize that. And I told you to take the tape off because it's dangerous. All right. I just can't do that, and I'm totally fine if somebody disagrees with me and you think that's a big deal and you should put that on there as well. That should be your choice or the client's choice. Me personally, the reason it's there, if I take that door off, I don't want to have a chance for that blower fan to kick on and me to be working anywhere near it and get sucked into it. That's the main reason. So here they're talking about the differences in temperature rise between older furnaces and newer furnaces. Most high efficiencies you're going to find are going to be somewhere around 25 to 55 degrees. And most of the older furnaces, those are going to be like 55 to 85 or, 65 to 95. I've seen them up there pretty high as far as the temperature differential that comes in there. So we use less energy, we use less BTUs because we absorb a higher percentage of the heat that we use. So we can use less gas and save more money. That's the whole purpose of the high efficiency. Going back to that though, if the whole purpose of having the high efficiency is to save the energy, then why would I want to take conditioned air from inside the house, use that to make the fire, and then just blow it outside the house? I'd rather get my combustion air, from outside the house and then blow it back to the outside. Charlie's 2 cents. So another term I want you to be aware of is something called orphaning a water heater. So in this one we have the round clay tile. That's where the furnace and the water heater originally went into. They ended up going with a high efficiency furnace. We can only see the pipes along the top on this one. All right. And so that's what these white pipes are up here. And then they ended up putting the vent connector going into the flue. Now, we can't use that big round clay tile for this many BTUs. So that, I think it's like a 3 or 4 inch vent connector that goes in there. Then that connects to a corrugated stainless steel. And I think the next slide shows it good. It really shouldn't even enlarge like it did here. They should use a smaller one so it's the same size going all the way up. But then this is what's called a flue liner that goes through the chimney and all the way out through the top. All right. So every mid-efficiency furnace that goes into a chimney, every high efficient, or every water heater that goes into the chimney by itself, they should all have flue liners. That's my 2 cents. And I'm going to call every single one of them that doesn't out. All right. The only ones that were allowed to go into these things were going to be the old natural draft furnaces, and we just don't see that anymore. Now, I hear a lot of arguments from heating contractors where you're allowed to discharge a mid-efficiency furnace if the fireplace is completely inside the house. So it's not on an outside wall. If it's completely inside, you could do that. Fine. All right. That may be true. I would have to see the manufacturer's installation instructions for that particular furnace. I would want to know. But if you're going to go that route, then you're also going to want to send a camera up that flue liner, because these clay tiles, when they had all that moisture and the temperature changes going on and off, they were just known to be cracking and mortar falling out of them. And now you got gaps in there that are going to let carbon monoxide enter the house. And I have been on a few homes where somebody put a brand new furnace in there. It was a mid-efficiency furnace that was in there, because of which the drafts moved slow. In fact, they weren't even enough heat because they put it into the old clay tile, couldn't get it all the way up and out. They didn't size it properly. And then all that carbon monoxide got stuck in there, and that was coming back into the house and was setting off the carbon monoxide alarms. All right. That was a big deal. And then we ended up tracing everything back to the furnace where it came by there, and all they had to do was drop a liner in here. Now, these liners aren't cheap. They look cheap, but they're not. Typically, you're looking at around $1,500, and this is the year 2020. I don't know how long this video is going to be around, and prices do go up. It's been pretty consistently, so I don't know where they're going to be in the future. But I do want you to know what a flue liner looks like, and again, that goes through and all the way up and out of the chimney. It's kind of a no-brainer. You see all that scorching in one spot. Hell, look at the size of that pilot light on there too. But nonetheless, this was a definite hole in the heat exchanger, and every time that blower fan kicked on, it was pushing the air out of the burner chamber. In this case, it was actually backdrafting there. Most of our backdrafting is going to occur at the top where the draft hood is, not down here. This is typically going to be flame rollout. But when you have such a isolated spot, it's that particular heat exchanger and that burner that was doing all the damage. It was, and you can see how, when fire grows or heat spreads, it goes up and out. So that's what we call the point of origin. And you can follow that V as it comes back in there, and that's going to show where everything is starting from. So here's another shot of a heat exchanger, a little diagram. We can see where our burners are going in. Heats up the inside. This is typically how the old Lennox natural draft heat exchangers were. They would go kind of like a hula back and forth, and the heat would bounce off of the different sides before they come back up in there to go ahead and create it. And it's that opening where the burner comes in that you look right on the underside of that, and that's where you find it. But again, we just don't see these anymore. I do want you, to realize that the circulation air blows on the outside of the metal, where the bad gases are on the inside of the metal. All right, going back with my airflow. So this is, and it doesn't matter if it's updraft, downflow, horizontal, I don't care. The order of flow is always going to be the same. Filter, fan, heat exchanger, and then at the top on the right picture is where my air conditioning coil would go if it was there. On the left picture, downflow furnace, filter, blower fan, heat exchanger, and if I had an air conditioning coil, it would be down at the bottom underneath the heat exchanger. We don't want to have our air conditioning coil before the heat exchanger, because that air conditioning coil creates a lot of condensation as well when it's running, and we don't want to blow that humidity over our heat exchanger, because that's going to cause it to corrode and rust out faster. Same thing, horizontal, left to right, filter, fan, heat exchanger. If I had an air conditioning coil, it would be on the right. All right. having these things operate and depressurizing a room, it does happen. It is rare. This is mostly going to be a problem on a natural draft furnace, not so much on a high efficiency or a mid efficiency furnace. But what we're talking about, and maybe the next slide will show this. Here's the blower door switch on this one. This blower door switch was just bypassed, and I do this. I take that door off and make sure the furnace shuts down. Just because the switch is there doesn't necessarily mean it's a problem. So going back to where that door was off and the blower door switches and the problems of depressurizing a room that I was talking about, this is the slide that I was kind of getting to. So if we look at this drawings on here, and this was an actual home, it was taken a long time ago, natural draft furnace. What's a common solution if you make the ductwork too small and you're restricting the airflow coming back to the rooms, and when I mean ductwork, I'm talking about the return ductwork, all right? Then that blower fan depressurizes that ductwork and causes them to collapse. And usually the fan builds up speed slowly, so the sucking in part is not as noticeable. But then when the fan turns off, you hear that big whoomp, and that's all the ductwork's coming back in there. So solution to that, and not a very good one, but it is a solution, is somebody can cut in those openings that we're seeing on the return duct where those two red arrows are pointing at. And that way we're not going to depressurize the rest of the ductwork. But then again, we're also not pulling air out of those rooms either. All right, so that's going to make the air circulation from the rooms less efficient as well. I know the solution is actually expensive, which means putting in bigger ductwork or additional ductwork in there, and that's not something that people normally want to spend. So they try to go ahead and find a solution. But here, in this situation, we're in a room where we were depressurizing that room. Now, if you look at the green circle, you can see all the corrosion and rust, and that negative pressure in there was causing this furnace to backdraft. And not only are we backdrafting, but now we're pulling all that carbon monoxide right into our circulation air, and we're just putting it into the house. This house did have a carbon monoxide alarm in it. It was going off, and this is what we determined to be the cause of that, is that the furnace was backdrafting and it was pulling the carbon monoxide into the circulation air until eventually it set off the carbon monoxide alarms. Clearances around most furnaces are going to be pretty much 0 or 1 inch, so they could be put into a tight box. Natural draft furnaces or mid-efficiency furnaces with open burners in the front of those burners we are typically going to be 6 inches, all right? And there's going to be a little chart on there where it talks about the left, the back, the front, the right, and so forth. And they talk about how many inches of separation. So this one, the very top of the furnace, they want you to have 1 inch. The front of it, because it's going to be a natural draft furnace, the 6 inches, so we don't block the air coming in there. Where it says vent and it says number 6, that's because it's gas. They're really talking about 6 inches around the vent connector for combustible materials. And then we could actually be touching the back and the sides to combustible materials. Here's another one, same thing. Sides 1 inch, back 0, front 6 inches, 6 inches around the vent or the vent connector, and the top again 1 inch. All right. Just want to know what all those numbers are for. Top 2, front 6, vent 6, rear 1, side 1. Different furnaces have different clearance issues, the combustibles. All right. We see this a lot in condos in the city of Chicago, and I don't know what to say with this. It's an old joke that Corey kind of told me about, and we kept it up there. It's called the Chicago squeeze. We're talking about the suburbs. They sell houses by the size of the square footage of the home. I swear that in Chicago, because they're all smaller and confined, that they're actually selling houses by the size of the square inch. So they do everything that they can to get as much space as possible. So they just compact all the utilities that are in there. But, let's use a little common sense here. I got a gas pipe that's going right in front of that blower compartment door. There's no way for me to get in there without dismantling this whole thing and doing any sort of work. That also goes in front of the return duct work, which just so happens to be where I get my filter out of there. This filter was never changed since it's been there because it's physically impossible to do so. All right, I would have to remove the washer-dryer combination, the water heater, all the gas piping, and everything else in there just to get to that furnace if I had to work on it. Not to mention, if that door is shut and I don't have any louvers on it, then the dryer's blowing air out. I'm going to be backdrafting my water heater, my furnace, if I don't have combustion air coming in there. It just has bad written in so many different areas. I have to say that with the newer condo constructions, I'm very happy to see that things are more spread out. They do bring in fresh air combustion. They are doing a lot of bringing in outside combustion air for furnaces and water heaters. So that part I'm pretty happy with. All right, a little bit on the burners. I'm not going to go real heavy. Typical manifold burners on here. Those orifices that I was talking about, they're going to be at the bottom. My device actually went dead, so I can't put a cursor on there. So where the manifold comes in there's going to be a small pinhole. That's the orifice. If I change this from gas to propane, that orifice has to be changed out as well. Larger opening for gas, smaller opening for propane. Those sliding tubes and the opening as I'm coming off the manifold, those are where I draw in my combustion air. All right, it's called Venturi tubes. So as the high pressure gas shoots in there, that creates a negative pressure around it, draws in fresh air and oxygen. These ribbon burners, typically, if they're working right, then they're going to be putting out a nice blue flame. So in the upper right corner of this slide, I would like you to look at some of those colors that are on there and just keep them in the back of your mind. Don't be surprised if you see a test questions on that. So natural gas, typically going to be blue, and there's going to be some pink or orange tips to it. LP is going to be more of a greenish tinge blue. When we're dealing with oil, it's going to be either orange-yellow or yellow-orange that's mixed in there. But most of the stuff we're going to have around here is going to be natural gas or propane. So it's going to be blue or green when we're dealing with it. Pilot lights coming on there. Sometimes we see silicon igniters. Sometimes we see pilot lights. Sometimes spark igniters. Different things that we're going to go ahead and start the fire. All right. When you hear the clicking coming out of a furnace, that's the spark igniter. This big gray box is actually what creates that and verifies that it's running. All right. So nowadays, everything kind of goes with these what I call glow plugs. So the proper term is a silicon igniter or heat igniter, hot surface ignition. All those are acceptable. When this thing starts up, it's going to glow bright orange. Then the computer is going to send gas in there. You can see the separation between the port and that tube, so the oxygen is going to mix in it, and that should ignite and getting everything lit up here pretty decently. All right. Monoport burners are found on just about every newer furnace that comes in here. All right. I hear a lot of people say that if the flame's blue, you can feel confident that it's tuned right. I think that's, when it loses its blue color, that means it's tuned really bad. All right. It doesn't mean it's tuned right. It's just not tuned bad, if that makes sense. Another furnace I'd like to chat a little bit about, and I've only seen 3 of these in my lifetime. They're called Pulse. They were made by Lennox. And then, so when we have our other furnace, we have a burner going inside there. We have heat exchangers in there. We have inducer fans and pressure differentials and a whole bunch of other stuff that comes in there. All right, to make it work. What Lennox did, was make a furnace using nothing but a combustion engine, for lack of a better term. In fact, that's exactly what this is a combustion engine. So it's going to send in gas, it's going to blow in oxygen, it's going to just like a spark plug and get an igniter going in there. That's going to explode, all right, just like a car engine does. And then it's going to go up and out through the tailpipe into something called a decoupler. And I think the next slide shows that, and we'll put it up in here. So you can see at the center piece that's kind of a cone shape item. You know, the gas and the air goes in there. We get our explosion. That's our primary heat exchanger. We get the tailpipe. That's actually number 2 heat exchanger. The decoupler, which keeps that pressure and removes the vibrating of the combustion engine. You know, that's the 3rd heat exchanger. And then that pressure, it creates a positive pressure inside this unit. That pressure now pushes all the gases through the coils, which is the same as we have for our air conditioning coil. And they're very efficient, all right? It's surprisingly quiet, and I don't know, the people that I see that have them, you know, the ones that are still working, you know, they love them, all right? They were very problematic. This is where you start seeing decouplers on ductwork, because these would vibrate when they would run, just like you would feel the vibrations of a lawnmower running. These would do that, and they would rattle the entire ductwork. So they would have to put their plenum up, and then they would put about an inch or 6 inches of I don't know, rubber ductwork or some sort on there. And so as that thing would vibrate, it wouldn't vibrate the rest of the ductwork in the house. And they would have to do the same thing with the return ductwork as well. That actually turned out to be a standard practice for a long time, and people were putting that in on many furnaces. But it's kind of gone by the wayside, and we don't see it anymore. And so that's called a Lennox Pulse. All right, it's literally a combustion engine. And like I said, 3 of them I saw in one house, and I was surprised that all 3 of them were working. I got to tell you, I was like a kid in a candy store. You know, when I saw this, I'm like, oh my God, it's a Pulse. And, you know, and I saw these diagrams so many times, and I knew what it was, and I was all happy and checked it out, and everything worked fine, and that was it. And the last one was in an inspection I did in Northbrook. We actually did a training class in there as well. And yeah, that was another one. They had a Lennox Pulse in there, and nobody seems to have the same dumb excitement that I have on this stuff. So enough of that. All right. So they were recalled in 82 to 89, models starting with GS, GSR. The reason why they were recalled, because these are condensing furnaces. They are high efficiency. They did have a high level of corrosion, which damaged that secondary heat exchanger. Again, best thing you could do, look on the floor of that blower fan, see if there's any water underneath there. And as long as there's an opening there, then it pumps out carbon monoxide, because it's a higher pressure inside the heat exchanger because of that combustion that's happening there. So it's able to pump out carbon monoxide, and that's obviously a problem. So, last thing we're going to chat about, and then I'm going to finish up here, is going to be filters. Again, I think I chatted on those before quite a bit. I can't encourage you enough to talk to your clients about the importance of changing out these filters, keeping them clean. This one actually got so dirty that it folded in on itself and collapsed. And we don't know how long this was like this, too. So remember the order of airflow, going back a little bit. Filter, fan, heat exchanger, and then the air conditioning coil. Now that air conditioning coil is, when it's running, it creates a lot of humidity because the air inside is humid. That coil is cold. Condensation is going to form on it. If I'm blowing that dirt over that wet area, that's just going to create a cake of mud. And if it gets to the point, because there's no way to get in there without dismantling everything, if that creates a cake of mud, then that's just going to stop my airflow. And now the only cure is to either take it apart and clean it, or remove everything and put a new air conditioning coil in there. Either way, it's not going to be cheap. Emptying refrigerant and putting it back in there is just not an affordable thing to do. So do everything you can to encourage your client to change their air filters. I know I sound like a broken wheel. I apologize for that. I just really think it's a minor thing, and it's really important to do that. I show them the sizes, show them the arrows, how to put it in there, especially if it's a first-time homeowner. And I try to feel the clients out a little bit if they know what they're doing. I'm not going to insult them by hounding on this. But if they're new and they got those bright-eyed looks in their eyes, then I'm definitely going to be talking with them. These cartridge filters that we're seeing more and more of, they're higher MERV. I'm hearing these things go for 6 months to a year. And I'll let them run until I get a bad temperature, rise out of these things. So, which reminds me, I'm due to change my air filter, and I better do it before Mrs. Belfontaine gets mad at me. So, electronic air filters, they also have certain directions. There's supposed to be pre-filters and post-filters. Those can come out and either be hosed off or put in dishwashers. I heard people get good luck with that. The other ones, it's nothing but a big bug zapper. So as the dust comes in there. There is a test button typically on the bottom of these things. So that when it does run, we could press it. And if it starts clicking, then we're good. All right. Pans. The only time we do not have to have a pan underneath the furnace is when we're in a basement or a concrete floor underneath, and there's no chance of doing any damage below the structure. But if there's wood frame or something like that, or it's on an upper floor, we want to be able to collect water from the high efficiency furnace, the humidifier, and the air conditioning unit. All those items can go ahead and create water, and if the condensate drains clog up, then we need to keep that from damaging the rest of the building. So, and we have to have either an alarm, some sort of cutoff switch, an auxiliary drain, something that's going to let us know that we have a problem and some action needs to be taken when we get up in there. All right. Electric heating elements, we don't run into these too often. Sometimes you'll see them in the ceiling, sometimes you'll see them in the floor. For those of you that are going to use thermal imagers, I love to do that, especially with those warm floors in the bathrooms and such. I'll just take a picture of the thermal imager. At least we know that it's working. All right. I'm not going to get into the sizes of anything else. Most of these aren't really meant to heat a room. Some of them are, mind you, but not those bathroom heaters. Those aren't really designed there. They're designed just to keep the floors warm, and that's about it. So, all right. A couple more slides, and we're going to wrap this up. All right. We do have to have a heat source in every room. So this is something that I see overlooked when we do our field training on some of these homes. We've had houses that didn't have a heat source at all in it, and it just wasn't recognized, because if we don't see it broken and it's just not there, it doesn't really look like a problem. If they do have a permanently installed electric baseboard heater, that's fine. That doesn't mean that a portable heat source is okay. It is not. It has to be permanent. All right. Typically, there's going to be a data plate on these things. If there isn't, then we got to guesstimate it. All right. So we want to have 7 is kind of an easy number to remember. All right. 7 watts per square foot when we come in there. So if I got a 150-foot room, multiply that by 7, is going to tell me how many watts I'm going to need from this room. The other thing is going to be a general rule of thumb. And let me skip over a little bit. This again is just general rule of thumb. We're going to say it's 250 watts for every linear foot, but whatever the data plate says first. All right. These things are all designed to keep a convection loop going into the room. So the bigger the room, the bigger the heating unit, and we don't want to have anything in front of it, such as couches or curtains or anything that's going to stop that convection loop. All right. If they are going to put curtains in there, keep it up higher. These electric ones, they get hot. I've seen these things at like 300 degrees. Because they get so hot, we're not allowed to put outlets, cords, plugs, anything on top of it. All right. So if it's an after effect where it was installed, that creates a problem in itself. All right. Now I've seen them where they're installed in them. That's fine. If it's hydronic heat, that's fine. But if it's an electric radiant baseboard heat, having an outlet over the top of it is not fine. All right. Caution high temperatures, keep cords, drapes, and everything else away. It does get hot. plain and simple. All right. And I think I'm going to stop here. We're going to, let me just see something real quick here. Yeah, just a few more slides. We'll get this out here. So when we're talking about the difference between gas appliances, we deal with BTUs. When we deal with electric appliances, we end up dealing with kilowatts that comes out of these things. There is an equation, I think it's at the very top, where it talks about the difference between the kilowatts and the BTUs and the size, but we don't really get into that. We want to make sure we get enough hot air flowing and check our temperature rises. The biggest problem with electric furnaces, especially in the summer months, we have trouble getting all the burners on, all right? So electric furnaces or electric forced air furnaces, they don't have, they don't all come on at the same time. There's a sequencer in there. So usually it takes about 4 or 5 minutes or more to go ahead and get all the heat going. But if the thermostat is going up and we're getting heat in there, sometimes they don't all turn on, plain and simple. They just use whatever burners are needed, to produce the amount of heat that's needed to get in there. So they recognize the amount of heat that's coming back in the return air, and they're able to see if they need to kick on another one and another one and another one where it comes to it. All right. One thing that is different about the electric forced air furnaces, these we do change the flow of air. So if I go back a slide, oops, I went too much. The gas furnace on the right, filter, fan, heat exchanger, air conditioner. With the electric furnaces, we're actually going to put the air conditioners before the electric furnaces. So the air conditioner comes first, then the filter, then the fan, and then I take that back. First it's the filter, then the air conditioner, then the blower fan, and then the heating coils. These are thicker and they're just not worried about being damaged from the air conditioning unit. All right. This is what one looks like. Me personally, it's a 240 volt appliance that I just would not touch. All right. It's going to be easy to get one of those cover plates and touch one of the heating elements, short the whole thing out. You're going to create one hell of a problem. So really the only thing we're going to want to do is turn it on and check for a temperature height. I got nothing else here that I can give you advice on that for it as well. So just do your temperature rise and that's about it. So I'm going to end this here, and I think I'm going to do, next week I'm not going to do anything, but the next one's going to be a hydronic system that comes in there. So for those of you that stayed with me this whole time, thank you. And I hope these are helpful. And again, they're going to be, I'm posting them up on our website as well at thehomeinspectors.com. It's going to be under the education and training, or under education and employment section. And you're welcome to review them over and over again, or they'll be here on this YouTube channel as well. And so I'm going to keep working on these things. And again, thank you. And that's it. All right. You guys have a good day.